Okay, good morning, ladies and gentlemen. Welcome to the opening ceremony of the FAPESP program on Quantum Technologies Initiative. And to open this event, I'd like to invite the president of FAPESP, Professor Marco Antônio Zago. I'd like to invite also the scientific director of FAPESP, Professor Marcio de Castro Silva, Filho. And joining the event online, the Secretary of Science and Technology for Digital Transformation of the Ministry of Science, Technology and Innovation, Dr. Ulisses Rosa. Please. And to open the ceremony, we give the floor to Professor Marco Antônio Zago, President of FAPESP.
Okay, good morning. Welcome to FAPESP. I'm very glad to be here in name of the Board of Trustees of FAPESP. We have defined a few strategic programs for the research agencies to develop in the next years. We decided that a few of our traditional strategic programs will have a continuity for the next years at least, such as the BIOTA, the research program on biodiversity, the program on global climate change, and the program on biofuels, known as BioN. It started as biofuels, and now it's focused on the question of renewables energies. So these programs, which are in place for at least 20 years, will have continuity in the next years. But we also decided to recommend to the scientific director that he should launch a few new challenges for our research community. And these includes all the questions related to digital transition and artificial intelligence. And the second important is a program on research on the South Ocean and Antarctic. And finally, a program on research on quantum technologies, quantum sciences. And the first movement came in the form of a white paper organized by a few competent researchers we have in the state of São Paulo. I'll say their names because it's worth saying. It's Celso Vilas Boas, Frederico Brito, Gustavo Wiederhecker, Marcelo Terra Cunha, Paulo Nussensweig, and Philippe QuTIa. These researchers organized a white paper summarizing the situation here in Brazil and especially in the state of São Paulo in relation to quantum technologies, and suggested that if we, FAPESP, should launch a program. And that's what is happening here today. So the Board of Trustees gave this suggestion, this orientation to the scientific director, and he, with his assessors, finally promoted this program, and I'll give him the opportunity to tell us what is the format of this program. I take the opportunity to greet also the Ulisses Rosa, which is the secretary from Science and Technology for Digital Transformation at the Ministry of Science, Technology and Innovation in Brazil. Also to greet the coordination of this new program, Gustavo Wiederhecker, Ben-Hur Viana Borges, and Felipe Franchini. Thank you. Have a good day work. Marcio.
Professor Marcio, the floor is yours.
Well, good morning, everyone, and welcome to FAPESP. Before getting started, I would like to greet Professor Marco Antônio Zago, President of FAPESP, my colleague Professor Carlos Américo Pacheco, President of FAPESP Executive Board, and also Dr. Ulisses Rosa, Secretary of Digital Transformation at the Ministry of Science, Technology, and Innovation, and Professor Gustavo Wiederhecker in the name of QuTIa Organizing Committee. So, dear participants, welcome to this very exciting event on quantum technologies, the launching of the QuTIa program. And we are delighted to have such a distinguished group of researchers and authorities gathered here today. It's really nice to see this outstanding initiative takes off. And this will be highlighted during Professor Wiederhecker presentation in a few minutes. So just to give you a briefly historical view of this program, after years of development, as Professor Zago just pointed out, this program was approved by the Board of Trustees of FAPESP by the end of last year. And already in April this year, we launched the International Young Investigator Award, which selected 5 grantees from around the world. And the next step, so in the first quarter of 2025, we will launch FAPESP, the Rio de Janeiro State Foundation, joint research grants with up to $1 million each, half of it funded by each state foundation. In addition to this, we will launch a FAPESP research consortium early next year, also in which up to 3 grants will be awarded to foster synergy and collaboration among research groups in São Paulo State. And this will be also highlighted by Professor Wiederhecker's presentation. Well, with that, I would like to thank you very much for being here, and I hope you enjoy this event. Thank you.
Thank you, Professor Marcio. Now give the floor to Dr. Ulisses Rosa from the Ministry of Science, Technology and Innovation of Brazil. Please, Ulisses.
Good morning, everyone. Are you listening to me?
Yes, we are.
Oh, perfect. Ladies and gentlemen, it's a great honor to be here today representing the Ministry of Science, Technology and Innovation, MCTI of Brazil, celebrating the formal launch of the FAPESP QuTIa program in quantum technologies. Quantum technologies are a vital component of Brazil's strategy for digital transformation, known as e-digital. This strategy aims to align the federal government's initiatives in the digital environment, leveraging the potential of digital technologies to promote sustainable and inclusive economic and social development. Within this context, quantum technologies stand out for their potential to revolutionize sectors such as communications, computing, and metrology, being identified as priority areas for research and development. The e-digital strategy comprises technological axes such as artificial intelligence, IoT, cybersecurity, and advanced communication. as well as business verticals focused on smart cities, agribusiness, health, Industry 4.0, and Tourism 4.0. The Ministry of Science, Technology and Innovation, MCTI, especially through the Secretariat for Science and Technology for Digital Transformation, has played a role in coordinating national efforts in quantum technologies, promoting research, development, and innovation projects, and strengthening the necessary infrastructure. Among the ministry's main actions, we can highlight the Quantum Technology Laboratory of the Brazilian Center for Research and Physics, CBPF, which received an investment of $7 million in the Quantum Technology Center and the Quantum Technology Center at FAPESP, with an investment of $4 million. The creation of Quantum Technologies Competence Center, led by Senai Cimatec, with an investment of approximately $12 million over 3 years. Public calls from National Council for Scientific and Technological Development, CNPq, to foster projects in quantum technologies with an investment of approximately $2 million. The Quantum Technologies Laboratory in the Center for Physics and the Quantum Technology FAPESP are the main important. The establishment of the Working Group of Quantum Technology, instituted to coordinate and align national initiatives in these emerging fields, with the participation of representatives of the ministry, research institutions working on the subject, and research funding agencies. The main objectives of the working group is to survey the quantum technology ecosystem scenario in Brazil, infrastructures, research, and teaching institutions and companies. Promote debate with stakeholders by collecting input, workshops, webinars, etc. Identify technologies and investment priorities. Identify gaps in training, infrastructure, research and development. Identify international cooperations. Identify public and private funding sources. And finally, prepare a final report with proposals for the Brazilian initiative in quantum initiatives. In light of this scenario, we have identified 3 areas as the most promising quantum tech is quantum computing, quantum communications, and quantum sensors. In summary, quantum technology represents a vast and promising field in which Brazil seeks to be at the forefront. Finally, I reiterate the invitation to FAPESP to participate in this national effort. Thank you very much.
Thank you, Ulisses. We now conclude our opening session, inviting Professors Zago and Marcio to take their seats in the audience. And hand over the coordination to Professor Gustavo Wiederhecker, the QuTIa Program Coordinator.
Obrigada, senhor Ulisses. Se o senhor quiser continuar.
Exatamente. Eu não vou colocar agora, eu vou deixar aqui.
Tá. Não, pode deixar projetado.
Ah,
não.
Okay, so now it's my great pleasure to introduce the first speaker, scientific speaker of this event, Professor Gerd Leuchs from the Max Planck Institute for the Science of Light in Erlangen. And should we? I need to please. So Professor Leuchs has a very long list of contributions, and I would exceed my times here if I were to list all the contributions he has made through the scientific community, including the quantum community in the world. But I would like to highlight that he's emeritus full professor of physics at the Institute of Optics, Information, Photonics at the University of Erlangen-Nuremberg. And since 2009, he's also a scientific member of the Max Planck Society. He's a founding director of the Max Planck Institute of Science of Light in Erlangen, and member of several academic societies throughout the world, including European Physical Society, the Optica, formerly known as Optical Society of America, American Association for Advancement of Science, and others. He has authored over 400 publications in this field and is recognized worldwide as a pioneer in the field of quantum technologies. He's also a recipient of the 2018 Herbert Walter Award from both the German Physical Society and Optica. And, you know, despite all this, Professor Leuchs, I was very lucky when I went for my exchange program during PhD funded by CAPES to be part of the Max Planck Research Group, which is sort of a trial period that the Max Planck Institutes go through before they are elected officially as an institute. And this was in Erlangen in 2006. And I had that picture over there because I wanted to stress a few things. So first was, I'm not sure if the picture's coming up. Do I need to do something? Okay, yeah, I'm not sure if Professor Leuchs is also seeing this picture, I hope so. So this is the picture at Hauptstrasse in Erlangen. And this was the day before the Bergfest, which is the second largest beer festival in Erlangen. Okay, so the whole institute would gather together to go there. This is one division of the institute, and Professor Leuchs might recognize a few faces here: Timon Elser, Markus Schmidt, Georgios Kakarantzas, and others that were part of this initial effort, and really their time there really reshaped their careers. Okay, and Professor Leuchs was always very open to, despite his busy roles, to just open his door for students to discuss science at the Institute. This is something I got only now to appreciate, of how time is constrained, and you're still open to welcome students to your office to spend time discussing pure physics. So yeah, without further ado, I'd like to open the floor for Professor Leuchs to deliver his talk. Thank you.
Obrigado, Gustavo, for this kind introduction and your kind words. What I prepared today is an introduction for non-specialists, so I hope there are non-specialists in the audience. Let me share my screen. Oops. So as a title, a very general title, I have the basics and promises of quantum technologies in a nutshell for the non-specialist. So this is just a slide showing you the website of the quantum flagship in Europe. And as a non-specialist, you might ask, what is so special about quantum? There are so many other things, non-quantum, what is special about quantum? And in quantum physics, we typically say we can have superpositions. A system can be in a superposition of different states. When the observer observes the system, some special things happen, which you have to get used to. And there is something called entanglement, so like an intimate correlation between things. And I'll try to walk you through this. So this superposition and entanglement is closely related. It means that a system can be in a superposition of different states, which, when you look at it with the eyes of a person on the street, you think this is strange because they seem to be contradicting. An example is Schrödinger's cat, which is simultaneously alive and dead. And the other thing is the effect that happens when you do a measurement. And while the superpositions, this is something which is not, you do not only find for quantum systems, you can find in many other systems. Every time you have some wave phenomena, you find this, for example. But the specifically quantum aspect is about what happens when you do a measurement. I will start with this. So my plan for today in this half hour is 2 items. To tell you a little bit what you should watch out for when you do a measurement. And the other thing is that when you do quantum calculations, things become a bit more complex. And if you have a product of two objects, A times B, that this is not necessarily the same as B times A. But mind you, this part it's important in quantum, but it's not specific for quantum. The specific part is the measurement. So let's start with the measurement. So suppose, I mean, all our intuition about waves come from water waves. Let's suppose we have a water wave. And I just sketched a wave packet here with an envelope that grows and decays, and you see this oscillation. So if this is a classical wave, you can take a camera, take a snapshot, and take a picture, no problem. So you see this wave packet, which is extended in space, and all the information can be read out. If you do a measurement with on a quantum system. Quantum systems are also described by a wave theory, so there are wave functions. Only these wave functions we cannot see with our eyes, unlike the water waves. And also these wave functions are somewhere inside the apparatus, so I just took some snapshot of many different components on a table, optical table in a lab. And so somewhere inside there is something that we would describe with a quantum wave function, and with some detectors and some electronics, eventually you can make it visible on a screen. So this is now our screen. So suppose we have such a wave, which could be like here, like something as a function of position. So horizontal axis could be position, for example. And then if you do a measurement, you will not see the wave in the way you saw it with the classical measurement. You will just see a signal at some point. Then you start all over again, repeat the same experiment, and you get another answer. And you repeat again, you get another answer, and so on. And eventually you can plot all the answers you got, and then the histogram of all of them, basically, then you will see, oh, there are spots which hardly ever appear. So this is probably where the wave has a 0. So what you measure here is the square of this wave. So you can see again an oscillation, but not in a single measurement, only after you have done many measurements. So the fact that despite of having a wave packet in the apparatus, you see only like one possible, this is like a signal for one possible position, although the wave is in many different positions. This, early on, it was called the collapse of the wave function. The more modern way to call it is a projection, a term coming from mathematics, which is more abstract, because collapse of wave function sounds like some dynamics as a function of time. And this projection seems to be, from all what we know, seems to be instantaneous. So you have this projection onto one of these several superimposed states. The superimposed states would be the system to be in one position or the other position or the other position, and you get only one of the answers. And then you repeat, you get another answer. So if you study physics and you work in the lab or in theory, so you have to get used to this. And you might ask yourself, I mean, is there any guidance, any hint? Can you help us how we can understand this? And in our everyday life, of course, we don't see things which are quantum so easily. Otherwise, we would be more used to it. So at first, I thought maybe I cannot offer anything, but then I was thinking I can offer you something from everyday life, which is not quantum, but which gives you a little bit of the flavor of what happens in a measurement. So mind you, in a measurement, you look at a wave function that is in a superposition that describes a superposition of many states, like different positions. And when you do the measurement, you get only one of these possible positions out. So in everyday life, we can have something similar if we take a picture of three-dimensional object and reduce the information such that this picture has overlap with two different interpretations, which are also mutually contradicting. I think many of you know there's a face of a young person where this is the chin and the nose and the ear, or the face of an older person where what was the chin before is now the nose, the necklace is now the mouth, and the chin is down here. And when you look at it, you can only see one. You can make it switch, but it's difficult. I think, I don't know anybody who sees both simultaneously. So the brain kind of picks out something that makes sense. So here you have a situation where you have more information in the picture than you can see at one instant in time. And I'm sure you know all these pictures. You can see a vase or two faces. But what I like better, because it's away from people, it's more abstract, I like a cube. So if you leave much of the information about the cube aside and only draw the edges of the cube, you can view it in two different positions, like in this one and in this one. And in quantum physics, we use these strange brackets to describe states. So here we would say what we see at the top is a superposition of a cube in this orientation and in this orientation, which is also contradicting. The cube cannot both be in the same way. So down here, I made the cube intransparent, so you only see the edges that you can see that are visible in an intransparent cube. And here this would be a transparent cube, right? So this is to help you to see the different orientations. So this is the best I can tell you, that when you look at this, there are two possible outcomes, either this or this, and you can see only one of them. And the brain, you can make your brain switch from one to the other. This is different from quantum physics. In quantum physics, when you have a detection of, you have the projection once, and then you cannot go backwards. So this picture, what I tell you, mind you, this is not quantum. It's the best that I can tell you to give you a little bit of flavor of what happens, that you kind of lose information about the system when you do a measurement because you project on only one possible outcome. Now, entanglement is this quantum feature which is important in many applications. This is about having several systems. Now again, we can use the same cube, we just take a few of them, and when you look at them, chances are that if you see this cube with this side being to the front, chances are when you switch over to the other cubes, this is the same. So it means each individually, you can flip your brain to go back and forth, but if you look at them jointly, they all seem to switch simultaneously. So you could say this is a superposition of all four cubes being in one orientation or in the other. So if you do a measurement on the first one, it will be completely undetermined what the outcome can be. It can be either one or the other. So this is a case where you have two possibilities. In general, you can have also many, sometimes infinite many possibilities in a particular quantum system. But to keep it simple, we We use here a case where you have two possibilities, and with 50% you have either of the two, so there's no way you can do a prediction. But when you do, so this is true for each of them individually. But if you do a first measurement on the first one, and then conditioned on this first measurement, you look at the second one, then you will see a strong correlation. So when you do this first measurement, so you can either see, you either get this cube or the cube on the right here. I hope you can see the mouse. It's either the cube which is pointing more towards the left here, and this cube is pointing towards the upper right, so you can see either of the two. Suppose you get this one, then you basically project onto this one state. Then obviously it cannot be this state, because this, in this case, the leftmost cube is pointing in a different direction. So this projection will project the superposition out to only one of the states. And now, conditioned on this first measurement, if you do a second measurement, you will see the third, you will see this, sorry, you will see the same orientation as for the first cube. So they are completely correlated. Chances are that if you would do it again, then this you would project onto the other orientation, but then the second measurement will also have the other orientation. So while the first measurement can be very uncertain, so this is the uncertainty and probability interpretation in quantum physics, but when you do this conditional measurement, you can have extremely strong correlation. And so this is important for applications. So as a summary, we can have certain mathematical complexity and superposition states. This you can have in all parts of physics, classical and quantum. And what happens in the projection, that is typically only for quantum, although we can take some guidance from these pictures where the brain flips, but this is only to help us. This is not truly quantum, of course. So in school you learn in quantum systems, this is wave or particle. I don't like this so much because I think it's more confusing. I would rather say there's wave and projection. You always have to, you're dealing with a wave theory, and the striking new thing is this projection that is happening. So the second topic is about this fact that A times B is not necessarily B times A. And in quantum physics, we have to work in higher dimensional spaces, which are difficult to visualize. So the highest dimension we can easily visualize is dimension 3, but this suffices for what I want to tell you. So these objects A and B in general can be can be rotations. So you have a three-dimensional space of objects, and then you can have some operations rotating a particular object in this space. And so suppose A and B are rotations, but around different rotation axes. So suppose A is a quarter rotation around the vertical axis, and B is a 90-degree rotation around one of the horizontal axes. And now I want to stop my screen. Can you see me? Let me see. Can you see me now? I want to demonstrate something to you.
Yes, we can.
Okay. So I have this beautiful toy which I got this was presented to me from a student from Pakistan I had at the time. So let's do this 2 rotations, 90 degrees. first around the horizontal axis, and then around the vertical axis. And remember what you see? So it's pointing downwards, you see the side. Now we do first the vertical axis, and then the horizontal axis, and you see something different. So the result is not the same. So that's the trick. And now let me share my slides again. Are my slides back, I hope? Do you see my slides again?
Yes, Professor.
Yeah, okay. So if you change the order of these two rotations, the result is not the same. So in quantum physics, this is the basis for Heisenberg uncertainty relation. So the fact I mentioned at the very beginning that this complexity, so if A times B is not the same as B times A, that means that calculations are not as easy as for normal numbers. This complexity you have in many parts in physics, whenever you are working in higher dimensions, and for basically all wave phenomena, if you have differential equations and the underlying space is a higher dimensional space, then you always run into this problem, which makes things more complex. So it is relevant for quantum physics, but it's also, you also find it in other parts of physics. Unlike this projection, what happens in the measurement, this is kind of a unique quantum property. So if you look at waves in general, then there's something which one calls conjugate variables like time and frequency, position and momentum, amplitude and phase. And basically they are connected by Fourier transformation. And so for such conjugate variables like time and frequency, there is something like a time bandwidth product. So the uncertainty in time and the uncertainty in frequency, or the widths of the frequency spectrum and the temporal pulse widths of the temporal pulse profile, the product has a lower bound. So this is typical in many cases in classical physics. Combined with the measurement process, you then get Heisenberg uncertainty relation. So Heisenberg uncertainty closely related, but it's something special because it is now also considering this projection that happens in quantum physics. So what does it mean, this time bandwidth product? It means if one of the two variables, let's call them Q and Q tilde, if one has a small variance and the other has a larger variance, then you can reduce this larger variance, but then the smaller variance will increase, such that the product of the two variances stays the same. You can also make this initially large variance even smaller, but then the variance of the conjugate variable has to grow even further. So on this slide, I show you that if you, I think even as non-specialist, you can see that if I have a wave which oscillates forever, then, oops, where's the mouse here? I hope you can see the mouse. I could probably go to laser pointer, maybe this is better. So this will be a wave which will oscillate from -infinity to +infinity. So now you have a very precise frequency. So basically this is a very narrow frequency distribution, but the time duration is infinitely long. If you add one more frequency, as a result of the superposition, you find a beating. So you will see the envelope go down and come back up again and so on. If you take 10 oscillating frequencies and you have one time where all the maxima overlap, Then if you add all of this, because of interference, destructive interference, you tend to have one peak, and the rest is much smaller because of negative interference. And if you take 20 oscillations, it becomes even more narrow, and away from the main peak, the excitation becomes smaller and smaller. So this is what I meant by time bandwidth product. If you want to have time very well defined, then you need many different frequencies. Okay, so applications. When you do sensing, and if in your sensor depends on only one of these conjugate variables, you can improve the sensitivity of your apparatus by reducing the variance of this variable. Of course, quantum physics tells you the conjugate variable has to have a wider and wider variance, but if this is not important for your measurement, you can win. So this is one possibility. Sometimes this is connected with the name of squeeze states because you squeeze the distribution function. Or you could say, I have entanglement. I mean, individually, the individual outcomes are very noisy, or I should probably say very uncertain. You can have one or the other of, in this case, two possible values, as we discussed before. But as we discussed, they're strongly correlated, which means that precise results are possible if you condition for the second measurement, which is conditioned on the first measurement. So in this, like this differential, if you look at the results differentially, you can have extremely precise answers, despite of the fact that you have this probabilistic quantum theory. And so this can be used for sensing, but it's also, this aspect is also, so the fact that quantum physics can give you extremely precise numbers under these conditions, this is also key to quantum computing. And let me look at the time, the last few slides, I want to tell you about this application. So in a classical calculator, you have input register, you have output register, and you have a processor that that calculates the output register that corresponds to the input register. So you put the certain numbers into the input register, and then the calculator calculates and gives you the output register. So if you want to know the output for all kinds of different input numbers, you have to repeat this as many times as you can have put numbers in here, which is like 10 to the power of the number of digits you have here. So this is 3, 5, this would be like 10 to the 10, right? Different numbers. And that can take time. Now in a quantum calculator, because of the possibility to have superpositions like you have in waves, because quantum physics is a wave theory, so you can have the input register in a superposition of all possible 10 to the, in this case, 10 to the 10 states, or in general, if you have m different different digits, 10 to the 10 states. And then if your quantum processor let it run once, then it will put input and output register into an entangled state, so that in the output register you have a superposition of all results. You might say, well, this doesn't help me much, but of course, because this is entangled, it means if you do a measurement on the input and the output register, you will get a pair which corresponds to each other, like one of the pairs that you can also calculate with the classical calculator. So only running the calculator only once gives you all possible results. So this is massively parallel and fantastic, and people thought this is really great. But as you already can see what is coming. This is only as long as you don't observe. If you look, so this is the entanglement. If you look, the projection will happen, and you'll go back to just one pair of one pair which belongs to each other. Same what you get in a single run of the classical computer. So you could visualize this in the following way. So the blue part is the processor. You have many different input values. And the quantum processor gives you the corresponding output values. This is massively parallel, but when you do a measurement, the projection gives you only one of the tracks, one of the connections between input and output register. So is there no way one can use this massive parallelism? Well, there is, and this is if you refrain from doing a measurement after you have entangled input and output register, but if you then do something so that all these, for example, let all these different outputs interfere, and then you'll do a measurement in the interference. And if then, again, projection allows you only to get one number, but if that one number gives you an advantage, then you have used this massive parallelism. So as an example, if you are not interested in the individual function values in the output register, but if the output register as a function of the input register will oscillate in an oscillatory way, and if what you need is just a period of this function, then you can, instead of doing a measurement, you can do a quantum Fourier transformation. And only after this quantum Fourier transformation, when you go into this into the frequency spectrum, then if this is a nice oscillatory curve in the frequency spectrum, you have a very singular distribution, and you will get typically one number, which is just the period. So then a single measurement suffices to get this period, for which in a classical computer you have to individually calculate all these functions and to then be able to determine the period. So then you can win. This is also the first application in quantum communication. So if you, when encoding information to have secrecy, people, for example, use the difficulty in finding periods of, finding factors of large numbers. So if the number is large enough, it takes forbiddingly long time to calculate the factors on a classical machine. But with this scheme, the quantum computer is very good at finding these periods. So there is an algorithm which was found by Peter Shor, where the complicated part relies on exactly determining the period of such a function, and this is why the quantum formalism wins. Other examples are, of course, if your quantum computer one-to-one kind of models a quantum system, which kind of behaves in a quantum wave in the first place. So if you want to get information about huge, big pharmaceutical molecules, for example, again, you have this massive parallelism when you do the calculation, but you know, it's just one number that you can get. But in such molecules, typically, maybe the configuration of the molecule is important, or related the ground state energy. So you're basically, in some cases, what you're really interested in is just one number, and like a global feature like this period, and then the quantum computer can be very helpful. So applications are in quantum computing. I'm coming to the end now. Quantum simulator, quantum sensing, quantum communication, and the systems that people study, the platforms, the hardware platforms, are superconducting circuits, trapped ions or atoms, semiconductor quantum dots, for example, or also photonic circuits. And so large companies have started to invest in this. As you may have read in the newspapers, there are many startups around the world. There are national projects. In Europe, we have also European projects. As I showed you the website of the Quantum Flagship. And so this is all going strong. This is the website of the German Ministry for Education and Research, and I'm glad to see that In Brazil, you also have some initiatives or some new initiative to do this, which is great because you have fantastic scientists in Brazil, especially also in this quantum science, quantum technology field. So my congratulations to having such a nice project. The next speaker, Chris Monroe, he will tell you about trapped ions, I guess. This is what his claim to fame. Thank you very much.
Thank you, Professor Leuchs, for this inspiring talk. There will be a question and answer session after Chris' talk, and Professor Leuchs will be back to participate in this. So I hope you had written down your most fundamental doubts about the quantum physics, so be able to ask yourself to Professor Leuchs about it. Thanks again, Leuchs, for taking your time to be here with us. Thank you very much.
Thank you.
So the next speaker today is Professor Chris Monroe. So I recovered this picture from a friend of Chris. I'm not going to tell who, but I think he'll be finding out after I introduce him. And Professor Chris is the Gilhully Family Presidential Distinguished Lecturer in Electrical and Computer Engineering and Physics at Duke University. He was formerly at College Park, Maryland, also as a professor, and where he worked as a fellow of the Joint Quantum Institute and Joint Center for Quantum Computer Science. So I would like just to add a few remarks about Chris, is that Chris did his PhD with Carl Wieman at Colorado, and Carl Wieman got the Nobel Prize in Physics in 2001 for condensates, together with other fellows. And I was looking up the Nobel Prize that Chris was involved later on under guidance of Dave Wineland, also at NIST, where he did his postdoc. And the Nobel Committee puts out a selection of papers that sort of guides the Nobel laureate decision. And there are 17 papers on this list. Out of the 17, 5 papers are Chris papers when he was working with Wineland. So I think if we were share, we would split by 3 the Nobel Prize, and I think it would be fair to say that Chris is certainly core to that demonstration. So it was basically, I think, arguably the most famous paper is a demonstration, the first demonstration ever of a fundamental quantum logic gate using trapped ions. So it's really an honor to have you here with us, Chris. And note about the picture, for those who don't know the involved there, you can see Dave Wineland in the back there with the big mustache. Wayne over there as well with the sunglasses. And on the left here, there's Flavio Cruz. So Flavio had this picture on his wall. So I was chatting with him about frequency comms recently, and I asked, who is this people in the picture? And he was explaining to me, and like, you see that guy in the red shirt over there? That's Chris Monroe. So this was, I think, 1995 at Boulder. I think this was a very productive time. And thank you, Chris, for being here with us today, and the floor is yours.
Okay, thank you very much. I presume everybody can hear me okay. So I'm glad to be here this morning. Good morning, everybody. Yeah, thank you, Gerd, for your talk. There will certainly be some overlap, but you know, when we all as scientists teach students, you know, repetition is always a very good thing. hearing things in maybe different languages, you know, different points of view. So indeed, I will talk about the subject of quantum computing, and it will be very general to begin with, but I will drill down into particular platforms with which we hope to build these machines. And again, a lot of the introduction you've just heard, you'll hear it again in maybe different words. Not only am I at Duke, I was co-founder of the company called IonQ. I'm no longer with the company, which is actually a good sign. They're well on their engineering phase and engineering path to building quantum computers. I'll briefly mention that. And that's actually one of the stories I want to tell you, is that we are getting into an engineering phase in this field, and industry really has to be involved. I mean, university, even though I'm a professor of electrical engineering and physics, universities don't do real engineering. We teach it, and we try to get things out into the commercial world. And I think quantum computing, you might argue how long it's going to take for it to become a commercial reality, but there are companies making big bets right now. And why is that? Because many feel that quantum computers are one option to continue our amazing growth in computing power over the last many decades, which is, I think we all know what Moore's law is, and this was sort of captures the amazing progress made in silicon fabrication, very large scale integration of silicon transistors. This plot here is a version of Moore's law that shows the transistor density on a chip over time. Note it's a log plot, so every vertical division is a factor of 10. And so since 1980, it's scaled to 1978 here, 1. And you can see since about 1978, things have grown exponentially over time. Roughly every few years, the transistor density doubles because they're getting smaller and smaller and smaller. Nowadays, this is even a little outdated. We're at the nanometer scale for individual transistors. A few nanometers is sort of the state of the art. And you can see why Moore's law is starting to taper, starting to saturate. And it's because it's getting too expensive to make things small, and actually they don't work very well when you get sub-nanometer. It's not only it's very hard to make, but a nanometer is the size of a very large molecule. And so transistors are approaching the granularity of matter, and so there's going to be a problem for sure. It might not be right now. We can squeeze more power out of our current systems. But Moore's law is ending, and quantum computing, it's a little bit an exaggeration to say quantum computers will continue us along its own Moore's law. Quantum computing is entirely different compared to classical computing, so it's very hard to compare the two, but there are opportunities. And remarkably, this opportunity was first mentioned a long time ago by Richard Feynman, and this is 60, almost 70 years ago. He was very interested in the birth of the solid state transistor, and he imagined that you could shrink these transistors down to be individual atom dimensions. And this quotation is really amazing. In 1959, he said, when you do that, many new things will happen because there are new opportunities for design, because there's new laws of physics going on at that level. And of course, the laws are quantum mechanics. And I would say, 40 years later in the 1990s, we learned that opportunity, it is quantum computing, almost certainly. The next slide, you might call this a pitch slide that you might give to an investor if you want to make a business. And there's some validity here as well. That is that when new technologies come along and they are so-called disruptive, it's not clear how they will play out. What might be clear, though, is that the companies making regular computers, maybe they're not the right companies to make quantum computers. So we're going to have new approaches, and in quantum especially, it's really exotic technology. I think Gerd touched on that in the last talk a little bit. So you might argue this is again a little bit exaggerated, a little bit overhyped, but if quantum computers are to be a next generation of computers, we really have to start embracing what they do and what they can be used for. So I'm going to skip really fast over the background. Most of you are scientists, and again, I can lean on Professor Leuchs' introductory talk on the field. But when I teach quantum mechanics these days, I teach it from an information perspective, from qubits, two-level systems. And of course, in quantum mechanics, we have 2 rules, and only 2 rules. They're actually not very hard. They're just conceptually challenging. And those 2 rules are, of course, the wave equation, allowing superpositions of information. This is sort of at the power of quantum computing. We can store things in parallel, as Professor Leuchs mentioned. Now, there is a wave equation behind a qubit here, represented as a superposition of 0 and 1. There's some complicated math, but it's very straightforward, actually. What's interesting, of course, is as you add qubits together, the state space, the number of configurations really grows. But that's rule number one. And as Professor Leuchs said, rule number one only works as long as it's not disturbed. And so we have to invent another rule that makes sense of these superpositions, because when you observe a superposition, it randomly collapses into one of its possibilities. So this to me is the weird feature of quantum mechanics, and that is that we have to use probabilities. These amplitudes A and B, they're actually probability waves. And the opportunity Feynman, I think, maybe had a hint on is that we can store lots of information in a quantum system, even if we can't directly get access to that information. Because you know, what good is a computer if you can't look at it? So the story of how a quantum computer works, I think of it as good news, bad news, and then finally good news. And that final piece of good news only occurred in the 1990s. Now, the first piece of good news happened in the 1920s or 1930s, that we have this theory, this wonderful theory of quantum mechanics that allows you to store superpositions. This is a 3-qubit superposition, and with 3 qubits, there are 8 possible states, and they're represented here with 8 amplitudes. These are probability waves, if you want. And again, there's a wave equation that tells you how these amplitudes behave. You can control them with a Hamiltonian, and this is a lot of what we do in teaching quantum mechanics and also building a quantum computer. We need to control the qubits without looking, without measuring. And in this box here, we're computing in massively parallel fashion. We're computing a function here, and we can use all 8 configurations, all 8 numbers, 0 through 7, and compute with one turn of the crank a massively parallel function. So that sounds great. With 3 qubits, it's not a big deal. 8 is not a big number. But with 300 qubits, for instance, the number of configurations is ridiculously high, 2 to the power 300. And this is more than the number of particles in the universe. Therefore, a classical computer will never be able to store or deal with 2 to the power 300 configurations at the same time. So this is great. This is amazing. This is Moore's law. Every time you add a qubit, you've doubled the configuration space. And that's the great news. Of course, the bad news is you have to look at it. And when you just compute any function and you then measure it, it's noisy. You don't know what function you're going to get, what value. It's totally random. So this is sort of useless for computing, because you pretty much have to repeat the process and keep measuring. And it's even worse than classical computing in a sense, because at least with a classical computer, there's a known function and a known output, and you read it out. Here, you're adding noise. Now, the final piece of good news, and this is largely due to David Deutsch in the 1990s and late 1980s, and that is we take advantage of the wave equation and the fact that these superpositions can interfere, and they can interfere almost completely destructively. And again, Professor Leuchs very nicely showed how this works. There are some problems that can be where we can control these interferences with quantum logic gates. That's the red dot here. This is very hard to draw, of course. And not with just 8 inputs, but you can imagine 2 to the power 300 inputs. Some problems, the interference can be so complete that when you make a measurement, you can get information on all of those inputs. And that's really what every useful quantum computation does this in some way. The problem is there's not many known algorithms that can take this form. The best known one is Shor's factoring algorithm, again, mentioned previously. This is the big one because you can prove how it works, and it basically factors numbers by using some number theory. It's actually a pretty straightforward idea, bringing number theory together with quantum physics, and importantly, it changes the complexity of factoring problems. If you have a big number you're going to factor, every time you add a digit to that number, it gets twice as hard. And so that's an exponential problem using classical algorithms. And of course, factoring is very important because it's behind crypto systems. You can factor numbers, you can break codes. So this is a very important application. It changes the complexity from exponential in the size of the number to polynomial in the size of the number. Now, keep in mind that factoring an interesting number it has to be really big, hundreds of digits. And we're not even close to quantum computers that can factor interesting numbers. That application is really far away, maybe even many decades away. Nevertheless, it's really important. So this is partly why countries across the world have national quantum initiatives to stay on top of this, because this application is super important politically. Now, there's another application that's not talked about as much, but it's also appropriate for quantum computers. That is optimization. When you optimize a function, you're finding one answer that depends on a lot of inputs. That's what quantum computers are good at. For instance, finding the highest peak in this mountainscape, well, it has two variables, latitude and longitude, and the highest peak, you can just see it. That's very easy. But if I give you a function, a complex function with 10,000 variables, you can't plot it, and it's very hard to find the maximum. So so-called optimization problems might be of interest to quantum computing. The traveling salesman problem here, a map of the United States, visiting a bunch of cities exactly once. What's the shortest possible path? This is known to be a very hard problem, a combinatorial optimization problem, classically. Quantum computers might be able to help. I think it's well established that quantum computers will not find the optimum, but it might do better than classical algorithms. So it's a so-called heuristic. You can't really prove how it will work. We have to test it. And the proof is in the pudding, as they say. If you find a path using a quantum computer, you can test, is it better than what my classical computer could do? More on the scientific side, there's another type of optimization. We don't call it optimization, but computing the structure of molecules. Electrons, in a sense, they minimize their free energy to determine the conformation of molecules. Even a molecule very important to Brazil, caffeine here. Caffeine has about 100 electrons. It's too hard to calculate where those 100 electrons wants to be, what their orbital states will be in a classical computer. A quantum computer might be able to map that problem. In fact, because this is a physics and chemistry problem, it's naturally quantum already. So the mapping to a quantum computer, it looks very promising. But again, nothing yet. We don't have these results yet, but these are some of the promising algorithms. So I'm one that actually, I know less about using them than building quantum computers. And so I'm very interested in the technology needed to build these machines. And as you can imagine, quantum computers are based on exotic laws of physics. So the systems that we build will also be exotic. This is from again, you don't need to read all the fine detail here, but there are several possibilities, several hardwares that look interesting. And this is adapted from an article in Science magazine about 8 years ago. And I list two columns here. On the right side here, these are generally solid state qubits, solid state substantiations of quantum bits. I call these synthetic qubits because they're man-made, they're fabricated. The most popular one being the superconducting junction that allows you to store, in a sense, a superposition of currents in a superconductor. And again, because it's a superconductor, nobody's looking. The electrons don't bump into things because they're in a superconducting state. Now, these qubits have huge challenges. Nobody really knows how to scale them, even though big companies like Google, Microsoft, IBM have invested billions of dollars into this technology. None of them know how to scale this. And the problem is quantum bits, that when you put many of them together, they become more and more fragile. They almost become self-aware. A big system is very hard to isolate. And these solid state systems also have to be kept nearly absolute zero temperature. And so you need to make bigger and bigger fridges. Nobody knows how to do that. Each qubit that's synthetically manufactured is different. That's a huge problem when you scale. Now, the left-hand side, I mean, the good news of these solid state qubits is that we have silicon processing. There's been many trillions of dollars put into very large scale integration that can be used, but it's very hard to get quantum physics to come out of those systems. On the other hand, over on the left here, we have what I call natural quantum bit systems: atoms, electrons, photons, individual molecules, individual atomic ions. These are quantum systems already given to us. They're sort of given to us by God. These are the qubits that already exist. The difficulty with these qubits is you need to isolate them, you need to control them, and therefore you need to electromagnetically trap them, isolate them. Photons are nice because they're already isolated. They can go through kilometers of fiber without loss, without being bumped into, without being observed. But photons are very poor memories because they go so fast. So it seems like we need to have some type of a matter qubit, and really the leading candidates are individual trapped ions. And there's a long storied history of laser cooling and manipulating atoms with electromagnetic fields. The point I want to make with this slide is that these natural qubits have a huge challenge, but it's not physics, it's engineering. And on the right-hand side, I would say, they have huge problems. I think they're really physics problems. Surfaces are noisy and it's very hard to make a beautiful surface. It's really not the engineering that's the problem, it's the physics. So I think they need breakthroughs over here. We don't need breakthroughs on the natural qubit side. So I'm very optimistic on the future of quantum computing using these technologies. And as I hinted earlier, big companies are sort of scared of these technologies. It looks a lot like physics to them. So the technology I'm very familiar with, individual atoms that are charged, these are trapped ions. This is a picture of about exactly 80 ytterbium ions that are trapped on top of this chip. The figure is expanded so you can see it, but they occupy about a 0.5 millimeter. That's 500 microns from left to right. And they sit right on top of this chip here. They're elevated by about 1/10 millimeter above the chip. The chip has about 100 electrodes. It's made by Sandia National Lab here in the US. There's nothing quantum about this chip. It's at room temperature. It's also in a vacuum. That's again, the exotic isolation we use with natural qubits is typically something like vacuum. But we can be at room temperature because the thermal isolation is very good. So how does a quantum computer work with one of these ion traps? Well, each ion here is envisioned to be a qubit. That might be obvious. And then the question is, how do you entangle them? How do you make gates? How do you get them to interact? Well, the qubits inside the atoms don't directly interact. These are like spin levels in the atom. The atoms are many microns apart. They're really far apart. We get them to interact through their Coulomb interaction. And we use lasers to do this. And so let me just show you an animation. This is a picture up here of a quantum circuit. It's a space-time diagram. Space vertically, there are only 7 qubits here, and time goes from left to right. And we want to run a circuit which involves a certain pattern of gates that entangles the atoms in a certain way. And in the 90s, this was pretty much finalized in how to make gates and circuits in trapped ions by Sirac and Zoller, and then later Molmer and Sorensen. And the idea in this circuit, we start with all the ions in an initialized state through optical pumping, standard atomic physics techniques. And then these gates are basically laser beams that poke individual atoms, and it actually pushes them around. They're optical tweezer beams that push them around, and they interact. And in this way, we can make gates and entanglement. We can program Shor's factoring algorithm in this way. By a certain pattern of gates. And then at the end of the day, my favorite part, we measure the qubits, and this is very simple. If an atom is fluorescing, it's one state. If it's dark, it's in the 0 state, a very direct type of measurement. Okay, so this is a very well-defined path to build a scalable quantum computer. And nobody really knows how to do something like this in a scalable way using solid-state systems. Now, I think the big companies are afraid of this technology because if you look at an atomic physics lab, it might look like this. This is my laboratory a long time ago at the University of Maryland. And again, a lot of optics. It's a mess. It's just a mess. And the action happens in a very small part of this table. Now, the good news is once you know what you want to build, you can engineer it. You can freeze the design and not use it so much for flexible research, but to do one particular thing. And so over the last many years, we put everything you saw on that table into a box. I sealed it up and made all the adjustments automatic that we need to. And without much exaggeration, everything here is inside this box. And this quantum computer right now, it sits a few floors beneath me in our basement, in our labs here at Duke University. And I mentioned vacuum chambers. My colleague, Jung-Sang Kim here at Duke, is very interested in engineering, miniaturizing devices used for atomic engineering. And this is a tiny vacuum chamber that seals right on top of the chip from Sandia that I told you earlier. So with a quantum computer like this, we can program it in a way that the user doesn't need to know what's inside. And to me, that's what makes any computer worthwhile, that the user doesn't have to know all the details. I mean, how often when we use our phones do we know exactly what's going on with the semiconductors inside? Well, never, hopefully. And so we have an opportunity to think about full stack quantum computing, not just the atomic hardware. This is sort of where I exist, but we have controllers for laser beams, compilers that compress circuits, and then a user might have an application they want to. They need to, the point is there are interactions, vertical interactions in the quantum computer stack that are really important and very hard, because we have physicists at the bottom here, engineers, computer scientists, and then maybe a biologist up here who has some application, or an economist who wants to optimize some model of the stock market. So it's a very fun field just because of all the interactions between these widely different fields. And let me, so this has allowed us over the last decade to do all kinds of collaborative work on quantum circuits. And one of my favorites I want to tell you about very briefly, it has to do with something called quantum scrambling. Scrambling is a concept of a quantum process that sort of, it's not just entanglement, but it's entanglement at all depths. And it's also in theories of black holes. It's thought to be a very important part of their dynamics. Again, I'm not a cosmologist, but people like Lenny Susskind and Benny Yoshida, some of my colleagues that work with us, they look at circuits like this, a 7-qubit circuit, and if you put some unitary process, some circuit in here, and you can do its inverse. If it's a circuit, that's easy to do. You can tell in this circuit whether this unitary scrambles or not, whether it entangles in a way or not. And it turns out in this circuit, U scrambles if that initial quantum state gets teleported to the last qubit. And you can test that. So this is a wonderful confluence of, I mean, we use atomic physics here to make the quantum computer, but this is, hitting different types of science. It's very exciting. And of course, these are the black holes, the 3-qubit black holes and their inverse. So it's a little bit of an abstraction, obviously, a lot of an abstraction. And you might know that there's a close connection between teleportation, quantum teleportation, which is a straightforward process of moving qubits around, and wormholes, communicating through wormholes. This is sort of amazing. And this is a very deep and almost philosophical connection that I find just fascinating. And we can even study, that we can think of studying dynamics of small black holes, theoretical black holes, using quantum computers is very fascinating. Again, I'm a little short on time. There's many experiments that test condensed matter models. In particular, this is a so-called SSH model of magnetism, where you expect to have some kind of an edge state, and we can program a long-range Ising model of magnetic interaction between these atoms. This is not exactly a quantum computation. It's more like a quantum simulation of a particular Hamiltonian, but I think of them in the same breath. And we can directly measure over time that an edge excitation lasts longer than one in the bulk. So again, sorry, covering that really fast. But needless to say, an interacting quantum bits can be used to simulate almost any interacting quantum system. And so it's being used for all kinds of fields in nuclear physics and as well. So before I stop, I wanted to touch on the company IonQ. I mentioned Jungsang Kim, my colleague here at Duke. He and I were approached by private investors many years ago that saw our research and said, oh, you should build a company out of this. And we basically said, no, we don't want to build a company. We're doing fine with our research. And they kept hounding us. And we eventually did this because our technology is sort of ready for that industrial engineering push. And in 2015, we founded the company. And remarkably, the company even went public in 2021. It's on the New York Stock Exchange. It's amazing how fast that went. And it has a several billion-dollar market capitalization. And we rang the bell on Wall Street up in Manhattan. And by going public, IonQ was able to prosecute and go after a very aggressive technical roadmap with a lot of funding. We've raised almost $1 billion in cash for IonQ to be able to hire engineers to build these ion trap systems so that they work without the user needing to know anything about atomic physics. This is probably typified best by our cloud systems And we have systems at IonQ that are available on the major cloud providers, so you can actually use these systems and program them. Now, the company wouldn't have existed without a vision to scale. And I showed you a picture of 80 atoms. That's not nearly enough to do anything interesting. We really need more like 800 or 8,000 or maybe 80,000 atoms. Well, we're not going to put them all in one trap. But we have this vision, and this is the paper that our investor likes so much. We have this modular vision of linking together multiple ion traps using optical photons and a multi-port optical switch. And so this, it's very easy to draw this in a slide, but we're doing all kinds of research in the protocols to move information from atoms to photons. And this optical switch is all classical. There's nothing quantum about an optical switch, and they exist. The quantum part are the atoms inside each quantum processor and the interface to the photons. And this is something Professor Leuchs knows a lot about, how to efficiently collect photons from atoms. So we rely on a lot of his work, seminal work, coupling single atoms to photon fields. That's a very important part of our scaling strategy. Now, what's important about this architecture is it's fully connected to scale, like a data center. If you have a bunch of individual quantum processors that are connected by an optical switch, you can entangle any pair of ions in the whole room without cost, without an additional cost over distance. So as we scale up, we're not going to be paying a price in time. The problem right now is that these photonic interfaces are still very slow. They're the bottleneck. And so again, here's where engineering is really going to help us. Integrated optics and all kinds of solutions like that. Now, as I conclude, I want to, again, be quite honest that this is a plot showing the number of quantum bits and the number of quantum operations you need to perform on those quantum bits. You need to do both. If you only have a few quantum bits, I don't care how clean they are, it's not interesting. With only 2 quantum bits, it doesn't matter how good they are. If you have 1,000,000 quantum bits, but you can only do 10 operations, who cares? You're not entangling the system enough. You need 1,000,000 quantum bits and 1,000,000 or maybe 1,000,000,000 operations on those quantum bits. And that's where all the opportunities lie. And again, as I hinted before, the factoring algorithm is way up here. We're really far away from that. But there are hints that there's some good stuff here because we can't simulate what goes on classically when you're up here. And we're just, I think on the verge of crossing these lines, depending on the technology. So this is to back out, it is a form of computing that's poised to capture the future of many problems that we don't solve, including those that are very important to national security and also future economies of the world. And the United States, like many other countries, have their quantum initiative. And I show this picture because I was roped into organizing the National Quantum Initiative here in the U.S. many years ago because I worked in Washington, D.C., I guess. It was easy for me to get to the Capitol every month. And so this endowed the big agencies in the U.S. with forming big quantum centers that are much more focused as they fund the development of these systems and technology transfer, getting technology out of the laboratory and into commercial activity. Although I will say, again, watch out when you read announcements from companies. There is a lot of hype there. Hype is not all bad. You have to have some hype, but you just be a little careful. So there's this interesting, I think, interplay, academic research and industrial development. There's sort of a big gap in how we communicate. But the commercial entities, they have to interest investors. So I sort of get they have to say things that are more bold than we would be comfortable saying in an academic setting. So my last slide here, at Duke, we have several researchers doing ion traps and neutral atoms. We're building several systems, and we're interested in this vertical stack. We have a lot of computer scientists, a lot of theorists, applications engineers, electrical engineers that control electromagnetic fields, RF, microwave, and optics to control these quantum bits and build systems. So it's not like we're a company, because I do believe that the role for the university is not to develop a commercial product, but to use these machines for science. And I think that can happen right now. It is happening right now. And this is really what's going to tide us over over the next decades before a commercial entity is actually going to make commercial value. And then the floodgates are going to fall, and it's going to be amazing. So with that, thanks for your attention. I'm glad to be here.
This was very illuminating, very, very nice work. So I think we go now for the Q&A session. So we have two persons helping us out, distributing the mics. So both Gerd and Chris can hear you. So I ask you to not start talking before you get your mic in hands. And who want to start?
Hi, I'm a physicist, and I have a question about the theory of quantum mechanics. So the theory of quantum mechanics was developed about the same time as the theory of general relativity. And there are lots of telescopes looking for deviations from general relativity. Are there any experiments looking for deviations of quantum mechanics?
Chris, shall I start?
Yeah, go ahead, Gerd, please.
Okay. Yeah, that's a good question. Of course, there have been many tests of quantum mechanics. As you know, after the basic equations were written down, first Schrödinger, which was non-relativistic, but then also Dirac equation, which was relativistic. I mean, within a few years, or even within an extremely short time, many things were calculated, and this new theory was applied to a wide variety of phenomena, and it's extremely remarkable how well quantum mechanics describes everything. So with our understanding about solid bodies and how matter holds together, and so all this is based on quantum mechanics. So it's extremely successful. So having said that, of course there are aspects you can check. So for example, in the measurement process, at the moment we think that this projection happens as fast as the detector can measure. This is why people went away from talking about the collapse of the wave function to projection, because there seems to be no internal time that the system takes to give the projection. Of course, to have some, like such a delta function, or like such a zero time response, or a zero response time, is you might think maybe this is not the final answer. So there are some people who worry about this and who think, how can one test this further? It could be that you have to go to timescales which are much shorter than what we can address so far. So all the experiments so far seem to be consistent with this projection being instantaneous. But this is something some people have in mind and look at, and there could be something new. It might be related to the question also: is space actually continuous, or is it ultimately kind of discrete, like on the scale of the Planck numbers? And the same maybe is for time. Maybe there is also a discrete. Maybe time is also not really continuous if you look much closer than how we can look so far. But this is at the moment this is speculating. I hope that helps a bit.
Thanks. Rodrigo, please.
Yes. So I have a question. Probably Professor Monroe can give us his views about that. That's more about the need of quantum error correction in the different platforms. So I don't know if you can comment a bit about that, particularly comparing the trapped ions with other platforms that have been always also showing some results in this sense. So that's it. Thank you.
Thank you. Good, very good question. And yeah, I didn't talk about error correction. I'm glad you asked the question. So error correction is actually a marvelous advent. Some people think it's more important than the factoring algorithm. The fact that you can error correct a quantum system, because again, if you have a quantum error, it's tantamount to looking at a quantum system, and that you lose coherence. But by redundantly encoding, by wasting qubits, you're not wasting them, but by having more qubits around, you can encode in a certain way, just like we do with classical codes. Now, with trapped ions, we don't really bother with error correction just because natively the idle errors of trapped ion qubits are very good. When we're not pushing these atoms with laser beams, there are no errors. But at some point, we have technical errors in our lasers, and by redundantly encoding, we can correct for that. So I estimate with trapped ions, error correction will only get useful when we have a few thousand trapped ion qubits, and we're not there yet, so we're not dealing with it. Now, other platforms, it's completely flipped. The synthetic qubits have intrinsic errors. They will lose coherence absolutely, even idle, after tens of microseconds. So you have to think about error correction right from the beginning in those platforms. And unfortunately, the bigger errors you have, the more overhead there is. And that's a real scaling nightmare. It's a problem. Now, academically, it's a very interesting topic, but in practice, the idea of a fully fault-tolerant quantum computer, we may never get that. We may never need it either. You only need a quantum computer to last as long as the problem you're solving. If it's fully fault-tolerant, it's sort of like a regular computer. We never use computers for 10 years at a time. So why would we build one that has an error-free rate for 10 solid years? So error correction is an interesting academic subject. It's very mathematical, but it should be tied to the hardware, the particular types of errors. They're biased. Errors have certain directions, and you can tailor your codes for that particular error. I think that error correcting codes that correct any kind of error that comes along are sort of useless. They're beautiful theoretical. It's like string theory. It's a beautiful theory, but totally useless. So I think error correction is a little bit overhyped right now. I think there are platforms that don't really need it yet.
Next question, Felipe.
Well, first of all, thank you very much for your nice talks. My question is about the access to quantum computer. Do you think that, in your point of view, that we will have access to a fault-tolerant quantum computer, or this kind of blockade that's appearing now, in some sense, will deny access for a high quality quantum computer? What do you think about it?
Maybe I'll take that quickly. Indeed, I think the technology will get there, where everybody can have access to quantum computers. I think it's more of a market question. I think in the 50, 60 years ago, people probably asked the same question about regular computers. The computer companies were making these big mainframes, and there wasn't a market for that many of them. And so it made sense to not have a computer in every home, but to have access to a cloud system. Now, if the market, if there are problems every day that you need to solve quantum computers for, the market will eventually miniaturize and invest in technology that makes it affordable to have them in your house. That's what happened with PCs in the 1970s and 1980s. Now, the second part of your question was a little more sinister, I guess, about will certain groups be blocked from using quantum computers? Indeed, for the cryptography application, there needs to be, that's important. And I think, fortunately, I think we'll get beyond that by adapting new standards of cryptography that are not susceptible to quantum hacks. That takes a long time to get there. And so it's going to, the transition time is going to be a little tricky. But I know in the US, I have to say that I'm very disappointed. The US, other countries are starting to export control. That is, control some of the technology that goes into quantum computers, the UK as well. I think this is really dangerous in terms of progress. in terms of research, because we love collaborations, international collaborations especially. I'm looking forward to collaborating with Vanderlei Bagnato, I have for many years, and some of his colleagues in San Carlos, for instance. We need to keep vigilant eye on the government that wants to control these things. And I think it's largely based on ignorance that they think they're going to have code breakers next week, when I think it's many decades away. And I think if they want to get there faster, we need to open this up. It's a research entity, and I think the best way to proceed is to have very open lanes of research. Maybe some countries would be off limits, but certainly nobody here in this room.
Hello, thanks for the talk. And I think my question is more geared to Christoph Monroe. Is that in the slide that you make the separation between the natural qubits and the synthetic qubits, you mentioned that for the synthetic qubits, maybe this became a physics problem. So I want you to elaborate more on that. Why exactly do you think that would be this new physics, at least as far as you think?
Well, I'll give you an example. There's this wonderful platform in solid diamond called the NV Center. This is a particular defect in diamond that looks a lot like an atom. It has a nitrogen atom instead of carbon, and next to it there's a vacancy, NV, nitrogen vacancy. Now that particular defect, it has beautiful properties. It almost looks like an atom that's in a solid state. You don't have to trap it; it's already trapped. This is a beautiful platform to build a quantum computer, except we don't really, it's very difficult to machine diamond and put these defects where you want them. And if you have a surface nearby, and there will always be a surface, the surface is not perfectly smooth. There might be oxides on the top, things like this. So there's a lot of physics, solid state physics, to get to, standing between this particular platform and a fully scalable quantum computer. And so I wouldn't exactly call it engineering. I think we need to maybe look at different classes of defects, different materials. That's materials science, condensed matter physics. We definitely need a breakthrough if we want to think about something like NV diamond as being a platform. So because there's a breakthrough involved, I mean, I guess there are engineering breakthroughs, but I think there's the more earth-shattering breakthroughs are scientific in nature, different ways of thinking about a material. And so that's sort of why I think that, we're not going to learn anything more about the atom in ion trap experiments. I mean, I think we know everything we want about the atom in terms of using it as a qubit. But so there's very little fundamental science to be had there on building the quantum computer. Whereas on the synthetic qubit side, we need new approaches. And this usually comes from a more fundamental scientific consideration of the platform. It's exciting.
Okay.
Very quick question. My name is Livio. I'm from CNRS, France, based here in Sao Paulo. I'm a silicon technologist, and I was very sensitive to the fact, Professor Monroe, that you started your presentation with the Moore law. So I would like to know if we can expect a Monroe law for the quantum technologies.
Another Moore law. It's slow and going. I think the number of qubits that we can completely control is slowly increasing every year. Moore's law is only Moore's law because there are use cases for computers. So I think in order to have something called a quantum Moore's law, it can't be just physics. It can't be just, we have another qubit here that works well in a physics lab. We have to have some application, and that's going to drive a Moore's law. I mean, Gordon Moore was the founder of Intel. He was with a company. So I think commercial activity in the long run is critical in this field in all respects, including having another quantum Moore's law.
Ario, please.
Yeah, I'm interested in the quantum simulation part. So you showed the slide in which there are simulations of the SSH Hamiltonian and so on. But I think it's fair to say that so far all these Hamiltonians and these numerosities are better reproduced on a classical computer rather than quantum. When do you think the thing will change and we will do physics using quantum computers rather than proof of principle?
Yeah, good question. We have other experiments and other groups do as well with, I don't know, 50 to 100 spins. These are long-range interacting spins, all-to-all magnetic couplings. There are certain phase transitions that don't exist in equilibrium, dynamical phase transitions. And where they occur, you can't predict because the Hilbert space is too big. So these are, in a sense, demonstrations because it's not a real material. It's not a standard model of a particular material. But you can't compute classically what's going to happen in these systems. We're already there, in a sense. But I think, as you're hinting, where are we? Well, we're able to simulate systems that nobody maybe cares about. It's more like a mathematics problem. So in some quantum simulations, we're already doing things that you can't simulate classically. The SSH model, that's a better known model. You're right, it's a small system. We only had 22 spins, and we could calculate indeed barely what the dynamics of that system, what was going on. You're right, and I feel a little disappointed to say that we're not, it's not quite there yet. But I think in the name of quantum computing, as we make bigger systems, I think I'm more interested actually in the science and pushing the scientific aspects of it and let the companies make commercial activities. So you're right, we're not quite there yet, but I think many different platforms. I didn't talk about neutral atoms at all. They have less control on the individual qubits, but they have many more atoms that they can deal with. So that looks very promising as well.
Okay, I have just one last question to both of you on your perspective on the workforce preparation. So you've both been involved in educational institutions that have pushed forward, even before this was a hype, right? The formation of grad students, postdoc, researchers in this area. Given the recent investments from public and private funding in this area, do you see there was a quantitative change in our capability of putting forward a larger amount of researchers and getting people ready to work in this quantum workforce necessary for developing the points you both raised so far?
Gerd, do you want to go?
No, okay. So as Chris said, we are not at the point when we have a big market and things are moving quickly, and you need many people to kind of like work on miniaturization, and so this hopefully this I'm sure will come at some point. We don't know exactly in which year, but at some point this will come. Currently the demand for the workforce is not as high as it will be in the future, but people are already thinking about preparing for the future, because I mean at the moment in all our universities many people hear physics lectures who are not majors in physics. So these are engineers, these are people in life sciences, and for them, I think quantum physics was not high on their list. So I think, and other people have said that too, it's important to bring quantum physics also to this agenda where physics exports physics lectures to nearby nearby fields, so that like the engineers who you then hire to build and to develop better devices, that they have a basic knowledge about what quantum physics is. So I think we have to prepare for the future and do this.
Okay, so I think we can close with that. I would like to thank again Professor Leuchs and Professor Monroe for for taking their time to spread the word about quantum technologies with us today. Let's give a last round of applause for them.
Obrigado.
Thank you.
Thank you. So I'd like to announce now we have the coffee break. We are about 28 minutes behind the schedule. So I would ask you to not dive too deep into the coffee so we can come back here and go for the final sessions. Thank you very much. everyone to the opening ceremony for the QuTIa program. Due to this sort of half an hour-ish delay we had in the schedule, I will use my superpowers to shift and invert the sequence of this event, because one of the Young Researcher Awards, which is what we really wanted to convey today, is attending from Finland. And if we don't do it now, he won't be able to be part of this. And I think that's more important than my talk about the program. So I'll flip the order. We're going to start off presenting to you with pitch talks, very short talks, just for you to get a grasp of what they are planning to do over the next 5 years. And we're going to start off with Dr. Rafael Barros, which has been recently hired at Physics Institute at the University of São Paulo, and we'll be talking about his plans for his Young Researcher grant. So they're going to put him online soon, and let's see if, okay, Rafael is already there. So Rafael, the floor is yours. Thank you for being here.
Yep. All right, thank you very much. Thank you for reshifting the program as well, and for the nice introduction. And thank you everybody for being there. It's really exciting to present the work to all of you. So I'll go straight to the topic. My proposal to the QuTIa program is called STRUCT, which stands for Deploying Structured Light for Quantum Technologies. I'm Dr. Rafael Barros. I work at the University of São Paulo, where I will be from January onwards, but right now I am here in the north, yes. So my proposal covers basically this part of the umbrella of the quantum communications, tackling problems such as the generation of photon pairs, entangled photon pairs, mainly for quantum key distribution, as well as hardware that is necessary for the implementation of quantum networks. But before going into a little bit more detail into the speech, into what I'm going to do exactly in São Paulo, I'm just going to briefly overview why it is so important to talk about quantum key distribution here. So in the previous talk, you guys already heard about the marvelous things that quantum computers can actually bring to humanity in general, but also there's a threat that comes with it, which is the threat to privacy. Right nowadays, most of the classical communications, they take place with public key encryption. And the way it works is, well, if Alice and Bob, two parties here, if they want to communicate a message, they have to encrypt their messages with keys that they share publicly. And then the messages that they actually want to exchange, they also exchange it publicly. And therefore, a possible eavesdropper, someone with malicious intentions, can actually intercept the messages and store them. Although, because it's so complex to decrypt with classical computers, it's nowadays still somewhat safe. However, this might not be true in the future, where there might be quantum computers, large scale, in the next decades, that can decrypt those messages. And the problem is that, although it might take some time until these messages can be decrypted by a quantum computer, nowadays already they can be stored, which is actually a problem for critical infrastructure, critical communication between governments and bank institutions, for example. So in general, we have to keep something in mind, that if the time that you want a message to be secure, plus the time that you need to migrate to a fully quantum network that is protected against quantum computers in a definitive manner, is larger than the time for a large quantum computer to be available, then you should worry about it. In this spirit, I am tackling with my program the migration to quantum networks in the state of São Paulo. The way I'm planning to do that is the following. I'm planning to tackle a plan that is divided in two parts. First, I want to initiate in the University of São Paulo a quantum structured light laboratory, an advanced quantum optics laboratory that is specialized in the hardware for quantum communication networks. And second, I want to implement the resources that we develop in this in the QS lab, in the quantum structured light laboratory, in the quantum network of São Paulo, one of the first quantum networks to be implemented in the country and in the state of São Paulo. So in the QS lab, my plan is to investigate the generation and the manipulation of faint quantum states, specifically entangled photon pairs, and to encode and read out information from these photons in the different degrees of freedom of light fields. And also to investigate how modern quantum technologies, such as photon number resolving detectors, can be used in the advantage of QKD and also quantum metrology. And with the resources developed in the laboratory, I plan to implement, as I mentioned, the quantum network of São Paulo, which has the topology there in the picture. So the plan is to do entanglement-based quantum key distribution, so distributing entangled photons across the states in the backbone of dark fibers of the University of São Paulo. So there are two main links that I plan to implement. One is a fiber-based link between different campuses of the university, starting from the University of São Carlos, or the Physics Institute of São Carlos, where we will install sources of entangled photons and send these photons through dark fibers to Ribeirão Preto and Piracicaba. And last but not least, there is also a plan for a free space channel right in the middle of the city. As you can see there, the view from the central campus of the University of São Paulo to the dense cityscape of São Paulo. But there are plans to how to overcome those challenges, and hopefully I'll be able to show you some results in the near future. So just in a nutshell, because the time is already out, so my project is then focused on basically developing new resource-efficient sources and detectors for QKD, for high-dimensional QKD, for example, using structured light, and to implement those resources that we develop directly into a deployed quantum network. And that's it. Thank you very much.
Thank you, Rafael. I think we're gonna pack the questions at the end. So thank you a lot. Thanks a lot, Rafael, for joining us. And just to close the Zoom sessions, I'll follow on with the other awardee that is also over Zoom, which is Hans Flores, which will be joining the Federal University of ABC. Do we have Hans online?
Oops. Yeah, you hear me?
Yes, we can hear you.
Okay, thanks.
Okay.
So I would like to greet the audience in the auditorium, and well, I'm glad to be part of this QuTIa program. And basically, the idea of the project is that is to develop an atomic magnetometer enhanced with a kind of light source, a quantum light source, which is squeezed light, as Professor Leuchs explained a bit earlier. And so why magnetometry? And just here. The motivation for this is that the atomic magnetometers they have gained attention because they have many applications in different areas. One of them is, for example, the study of the brain function, in which, for instance, our neurons, they produce tiny currents, and this generates very weak magnetic fields. And for some time, these kind of signals were detected with the squid sensors, which are inside a machine like this one. I hope you can see the mouse here. And let me see if, yeah, like this one, right? And so these sensors, they have high sensitivity, but at the same time, they have a very high cost of operation, because these sensors, they need to operate in cryogenic cooling the system. So, Professor Matt Brooks and colleagues at the University of Nottingham, they showed that actually you can use atomic magnetometers like this one, like those you can see here, and this size, and they have high sensitivity, high sample rate, and a very low cost of operation compared to the squid sensors. This is not the only application. There are many other applications like magnetic imaging to detect objects behind metallic enclosures, or also use them for battery diagnosis, in which the idea is to detect defects on the fabrication of batteries without using X-rays. Or more recently, for instance, there are proposals on doing magnetic communication using these magnetic sensors in situations in which the standard radio frequency communication fails, like in underwater situations. And more recently, there is a way of, or there is a search for action-like particles, in which the idea is to use magnetometers coupled to noble gases and trying to see these exotic physics with these kind of sensors. So the sensors that have been developed so far, they are scalar magnetometers. And basically, this is the case in which light prepares the atomic spins, and in presence of the magnetic field, they start processing. Problem is that they are scalar, so they only are sensitive to the strength of the magnetic field, but they are not sensitive to the direction so far. But ideally, there are some applications in which it is important to know the direction of the magnetic field, right? In some applications in detecting studying the brain function, there are some applications in which it's interesting to know the direction or the different components of the magnetic field. And so such that if the magnetic field is tilted, then as in this case, right, the spins, they follow the direction of the magnetic field. So this is what we did in collaboration with Professor Thomas Fernholz and Thaddeus Piderius at the University of Nottingham. We developed this technique of using, of having a vector magnetometer. But we had, our demonstration had a limited sensitivity, right? So the idea of the project is to develop a vector magnetometer, but with a better sensitivity, and that involves to work on the atomic sensor itself, right? Or also another way to increase the sensitivity would be to use another kind of light source, which would be a squeeze light, right? So regarding the atomic sensor itself, the idea is to use a kind of vapor cell that uses buffer gas, which is a gas inside the vapor cell that preserves the spins of the atoms as they propagate within the cell. So with this kind of cell, we can increase the density, the atomic density, and also the sensitivity. Another point that we want to work on is not only work on one species, but working with another species like cesium. It is useful also to increase the sensitivity of the sensor. And the other aspect of the project is to implement this vector magnetometer technique, not in a standard vapor cells of 1 centimeter size like this one, but to implement it in microfabricated cells like this one. Because since the idea is to do small sensors, to do this kind of studies, it would be important to implement this kind of technique in small sensors and microfabricated cells. So, and regarding the light source, which is then the other part of the project, in order to produce a squeeze light, so far it's been demonstrated to use it with very complex systems in which there are several processes like second harmonic generation to pump an OPO with crystals, and then it really produces the squeeze light. But what if we use the atoms themselves inside a cavity to produce the squeeze light? And so that's what we demonstrated in collaboration with Professor Marcelo Martinelli at USP and Professor Alberto Marino at the University of Oklahoma. And we showed that it is possible then to put the atoms, here you see the atoms inside the cavity, the mirrors, and when you pump light into it, then it produces a squeeze light. The advantage of this system is that it can work with at least 25% of the power compared to the system when you don't work with the mirrors, which is an OPA, basically. So the OPA usually works at this range of power, and with the OPO we can reduce the power of operation at least 25% of power. And well, we show that we can produce a squeeze light. So, but the other point is that if we are saying that we can work with not only with the rubidium, but with other species like cesium, try to produce a squeeze light for cesium is a bit more tricky because it involves complex or systems with more optical elements, and that involves complexity on the system. And but with the OPO, the nice thing is that it's a compact system that you just need to do modifications on the cavity and still pump and work with cesium. And ultimately, the idea would be then to have the same system that can work with rubidium, so such that you pump light to the atoms and you produce the squeeze light for rubidium, or you can pump light for cesium, right? And you can produce a squeeze light for cesium with the same system. But we can also leverage the possibility of having a vapor cell with a mixture of them. So we can work with a vapor cell with rubidium and cesium, such that if we pump with the two wavelengths that correspond to these atoms, then we can simultaneously have a light source that produces a squeeze light for rubidium and for cesium. So this is the other system. The idea is to develop during the project. And then the idea is to take this light and read the magnetometer with this kind of light, right? So this is a project that is going to be developed at the university, at the Federal University of ABC, at the Lab of Optical Spectroscopy and Electronics. And the project will offer some one postdoc fellowship and 2 PhD fellowships and 2 undergrad scientific initiation fellowships. And so in conclusion, the idea is to develop the first atomic magnetometer in Brazil that involves also to develop a new kind of light source like this one of double OPO with that can run or that can produce a squeeze light simultaneously for 2 different atomic species. And well, the idea is to open this new line of research working with hot atomic vapors to develop quantum sensors and contribute to the background of the undergrad students in this kind of area. So thank you very much.
Thank you, Hans. Now I'm going to invite the ones that are here. I can start with Rodrigo Benevides. He will be joining also Institute of Physics at the University of São Paulo. He's coming from ETH in Zurich, I guess, right?
Okay, well, good morning, everyone. Let me just... So first of all, I would like to say that's a great privilege to be part of this group of scientists who will be dealing with the challenge of bringing more quantum, advancing different fields of quantum technologies here in the state of São Paulo, right? And in my case, our team will be dealing with this project here. We will try to build a modular microwave to optical quantum transducer. And to get there, to understand what I mean by that, I'd like to bring this picture from a new result from Google Quantum AI that was released conveniently for me just like a couple of days ago, of their new advances in the area of superconducting qubits. And they have done this system where they can basically prove that increasing the size of their system, they got better, decreased the error rate of their logical qubits that they were doing there, they were making there. And all of this based on superconducting qubits technology. That's why it's clear now, it's one of the many examples that show that superconducting qubits are a very mature already technology to make quantum computing. And when we look at them, we can take a closer look at this device, and we see that these superconducting qubits are basically microstructured electrical circuits where we have given transitions that we can engineer, for example, in the order of a few gigahertz. And to operate these devices in the quantum ground state, we normally need to operate them inside these dilution refrigerators that bring the, can you see the mouse? Where is the mouse here? That bring our temperatures to very low ranges. That gives also us the quantum ground state of the system. If you want somehow to make a quantum network now with this device connecting 2 or more of these quantum processing units, we face now a very big challenge. We could naively try to directly connect this device using SMA cables and keep the same frequency range to make these transmissions. However, if you look at what happens at these frequencies at room temperatures, we see that it basically forbids us to accessing more complex quantum protocols in this range of temperatures. That's why there's a big effort in the community to try to integrate superconducting qubits with the more standard transmission technologies that we have, that are the optical fibers, that naturally are operated in the ground state because of their high frequencies. Once we get there, once the field can reach this goal, there's a lot of possible experiments that come up out of this. I just list a few, but it's really a very rich area. In this field, it has been shown, a few things have already been shown. For example, I summarized then in like some modifications in the optical signal depending on what we do in the superconducting qubit, like we can see here in these 2 results, where by changing the superconducting qubit, they can see some Rabi oscillations in the optical signal. And it has also been shown some 2-mode squeezing between microwave and optical systems at the same time. What has not been shown that we will try to aim for in this project is the direct transduction of states from one regime to the other, right? So basically, this is the general goal of our project. To go first from microwave to optics and the reverse problem as well. For that, we are proposing to work towards this device that includes basically a modular approach that will ease basically the construction of such a complicated system. We'll have a chip that will be composed of a superconducting qubit, electromechanically coupled to a mechanical surface acoustic wave platform here that can bring now the information to an optical cavity where we can use optomechanics to read out the information. So the idea is you can go both ways here, both entering with optical signals or entering the microwave signals and doing a both-way transduction here. For that, we are starting a new lab at the University of São Paulo inside the Institute of Physics. We are naming it ECHOS, that stands for Engineered Quantum Communication Systems. This will bring us the basic infrastructure that we'll build there. We will include a dilution refrigerator. That's basically the core of our system where all of these experiments will be running. We will have a lot of all the basic radio frequency and qubit control tools that we'll need to operate these qubits. Also the basic optical setups that will allow us to make the optomechanical interactions. And the microfabrication will be focused mostly at the University of São Paulo. It will be done mostly at the University of São Paulo in the Polytechnical School, but also with some connection with the University of Campinas and potential collaborations as well with the BPF now that they have a very nice infrastructure there as well. With that, I'd like to acknowledge, first of all, FAPESP, of course, for the support of this project, FUSP as well, because of all the institutional support, and particularly to QuTIa committee for all the effort done to help us doing that. And thank you all for listening to us.
Amilson, do you want to start? So Amilson Frisch is starting his project at the Institute of Physics at São Carlos, University of São Paulo. He was previously at the Joint Quantum Institute in Maryland.
So, is it there? No. Okay. So thanks everyone for let me show my work here. And first, a big thanks to everyone from working on behalf of FAPESP and the committee that to accept my proposal also. So my proposal here for this project is to build an ion trap that's mostly, as for example, we had a very nice talk of Chris Monroe before me. And this is a project that he's going to collaborate with us. Of course, we are starting this project, so I propose not only I'm going to build a quantum computer, but also this ion trap is a versatile machine that can be used for different type of experiments, and one of them will be for metrology. Okay, so I just put a brief introduction. I didn't know actually what other people will talk about, but basically here is just a single slide comparing classical versus quantum computer. And this is just to mention that for everything that we note in classical computer is represented by these binary ones and zeros. And here, just to give some idea that how everything is written, is I just put like FAPESP written here. And as you can see that a couple letters becomes a lot of numbers. So it's probably you can see that if you write a single page in letters, this will become a book in numbers in this binary representation. But this is not a problem for classical computers. And things that they didn't touch is actually how something that we can use, that's Monroe talked about a little bit this as use atoms as for a quantum computer. And so as we know, a quantum computer works with quantum bits, and quantum bits, the advantage is we can use this property of quantum mechanics that they can be in a superposition of different states. And one of the simple example that you can show this, for example, is a two-level system atom that you couple with the external light. So if you have an atom in the ground state, you couple to an external light, you can make the transitions from the ground state to the excited state, and it depends on the pulse duration. So if you make like the correct pulse duration, you can transfer all population to the excited state or not, or going back and forth between them. And you can see that in the middle you have everything becomes probability. So you have probability to find the atom in the excited states, you have probability to find the ground state, and in the middle you have some distribution that you don't know exactly before you do the measurements. And I'm glad we had a presentation about these superqubits, superconductor qubits. And here's just to give some example of how quantum computer looks like. So it's not single device like you put in a table. Right now, my experiment I'm gonna build looks more or less like this, in a more compact way these days, like Chris showed before. But the idea is that you can use charged particles to trap them individually by using these trapping ions. And there's all advantages and disadvantages in most of them. So this is one example that people use superconducting qubits, and this is what big companies normally have. And most recent people start to use one promising system, that's these neutral atoms in optical tweezers. This, in terms of the system, is very similar to what you have in the first four ions. You have a lot of optic tables, and a lot of device to control these ions with a very, very nice precision. So then how this, you see like everything is big here, but all the things happens in a very small region. That's the device where you can use to trap the ions. So the idea here is very simple, is that if you have a charged particles, you can use the electric field to basically push and pull the particle to a region where we can confine. So if you do this in the right way, so you have you can find a string of different ions, and basically, as Chris showed before, the problem is not to trap many ions. You can put 50, 70 here, but the way you control this, it's something that you need to do very well. And well, so this is the system that I decided to do, although I have also background in cold atom, in neutral atoms, but this seems to be a more, something that is not just a promise, but it's something real that people are using. And once I decided to do this, the idea was say, I'm starting with this experiment. I'm sure that most of us will have some ideas based on the other experiments. And for me, what looks like pretty cool is the Rainer Black group in Innsbruck, that they have these ion traps working for many, many years. And they have built like many different versions. So what Chris Monroe showed to us like is a very beautiful trap, but the problem is that we don't have like infrastructure in Brazil to do this kind of fancy traps yet. So I will probably spend like 5 years designing the trap and maybe nothing really working in physics. So I decided to go with this type of trap here. So we did the first technical drawing of this version. And last week we started to do the printing. And as you can see like this, there's nothing really fancy on doing these traps if you want to do these traps like this. But then based on this here with machining normal techniques or common techniques, we can do this in a device that some of the parts are shown here. And one of the blades are missing is just because we took one of them for this machine shop for them to be able to see what this looks like. Okay. Okay, so then once I have the trap, to talk a little bit more about physics, I need to talk about the atom that I choose to do. So here we have strontium atoms. And the good thing that what people use this for quantum computing is because they have like a very narrow transition here. That's I highlight in red. This is a very narrow transition, so it's challenging to address. You need a very stable lasers, optical cavities, and everything. But once you do this, you don't only do quantum computing. You actually have a very good measurement of frequency, and then you can use for different type of physics, for sensing, or many other applications. And one of the things that I choose is to do also metrology, because this actually works as optical clocks. And we have at University of São Carlos, University of São Paulo, the Institute of Physics in São Carlos, we have a group working on atomic clocks. So they have already infrastructure. So if we propose to build an optical clock, we already have all the infrastructure to collaborate with some patterns or some standards. Okay, and something that is new, I would say, like in this field, is to use another isotope that is the strontium 87. And the new things about this is that we have some ideas of these, like in this precise measurement physics, nobody ever measured this transition, the hyperfine states. So these you can do qubits, optical qubits using this transition, but also if you use different atoms or different species, you can have access to this nice transition that is gigahertz. So with this you have like very nice compact systems to assess this transition here. And one of the things you can do is to explore this very nice measurement of this transition that I'm sure, to the best that I know, nobody ever measured with very, very high precision. Okay, so thanks everyone.
Okay, now the last but not least, Simon Silva is joining the Physics Institute at Unicamp for developing quantum dots coming from the Kleppner Institute in Austria, right?
Okay, thank you very much for having this opportunity to bring this research line to Brazil. And the title of my project is Solid State Single Photon Source for Telecom Frequency. I want to start this presentation with a short introduction because I think it is very important why I reach now this stage. And I started my studies in Universidade Federal de Viçosa. During my master degree, I started to work with molecular beam epitaxy, and in 2013, I moved to Campinas to work in the Laboratório Nacional de Nanotecnologia, LN Nano, with Professor Christopher Denick. And in this PhD, I have the opportunity to help him to build up the 3.5 molecular beam epitaxy system that is in the Nano that you can see here in this picture. And because of this gave me a lot of experience in crystal growth and also in the instrumentation behind the molecular beam epitaxy. Because of this opened the doors for me to move to Austria in 2017 to work in the group of Professor Armando Rastelli that is well known in Europe by the use of gallium arsenide, aluminium gallium arsenide quantum dots grow by molecular beam epitaxy using local droplet etching. And during the 7 years, I was involved in a lot of projects, and each of these projects bring these quantum dots almost close to the generation of ideal single photon source and tangle photon pairs for quantum technology applications. Okay, this brings me to the main objective of my work, that is develop a new single photon source, a deterministic source of single photons that can operate in the telecom wavelength. And here you can see a picture of a graph of energy gap by lattice parameter, lattice constant, and you can see that the system that I was working here is this system here, aluminium arsenide, gallium arsenide. And the advantage of this system is that if you see the lattice parameter, it's almost the same, what makes this system very suitable to grow high quality heterostructures. And this is influence in the optical properties of our single photon source. The only problem about this system is that the emission wavelength is very restricted to 800 nanometers. And if you play a little with indium and grow these quantum dots with indium inside, we can extend this emission wavelength to 900 nanometers. But in a near future, if you want to build up a real quantum communication channel, it will be very suitable if you can use the well-established optical fiber network that is around the world. But the main problem of this gallium arsenide quantum dots is that the emission wavelength is here in this first window, where the attenuation in optical fibers is very high. And basically, this comes from the objective of my work. I want to use all my experience in the growth of gallium arsenide by local droplet etching for the aluminum gallium arsenide system and transfer this knowledge for the antimonide system. As you can see here, also the indium arsenide, gallium antimonide, and aluminum antimonide system have almost the same lattice parameter, and it's a well-established system that people are using in the industry to grow infrared detectors. And with antimon inside my quantum dots, I can build up a single photon source that can operate in the telecom regime here in 1500. And the most important about my work is not about growing this single photon source, but it's about bringing off system, a molecular beam epitaxy system for the state of São Paulo that we can provide high quality heterostructure samples, not only for my research, but for the research here in São Paulo or in Brazil. Okay, I'm a bit nervous, sorry, thank you very much.
I'm not sure if we still have Rafael on Zoom. I think we have Hans. So in the interest of time, I'd like to keep this relatively short, but I would like to welcome you to make any questions you may want to these young fellows that will be leading São Paulo quantum technologies for the next 5 years. They can answer, you can try.
Hello, I'm Matheus. I work in Unesp, Araraquara, Institute of Química, and I want to know, you are doing hardware. Who are working the software? Who are programming the software that coordinates, integrates the software and operational system that enable anyone to work in that, and we can elaborate more algorithms that became that useful. I'm not hearing, sorry.
Yeah, take the mic.
Sure. We were not sure for whom you were asking to, but or everyone.
Yeah, just go ahead.
I'm you want to know because I'm a system analyst. My work is programming, not building the hardware. So I'm interested in scholarship that belongs to that kind of work.
Yeah.
You know?
So I think this is a quite wide question in the end, because like there's, yes, you are right. We are working more in the hardware perspective of it, right? And I believe that there's a lot of challenge already there. And the idea is that at some point, I don't know if necessarily us, but like the community should bring together also computer scientists and people already like that have more experience in the algorithm part, but that can somehow communicate, and we should find a common ground, you know, like, because honestly, I know little about algorithms in a more structured level, right? Like I know in my daily life in the lab, but for sure when we go for real implementations, once we have, please, let's pray, once we have working quantum computers here in the state as well, you know, like we need to integrate, but at this very moment, I feel that we are still at the stage of setting the ground of the hardware of what we can do here. And then I imagine there are also other groups doing more like just the algorithm part, you know, like there are some groups also working more in the theoretical perspective. And at some point, I imagine that we can merge together these ideas. But maybe someone else also has ideas about that. Like
yeah,
Felipe,
I just
right?
want to contribute to the answer, because in the state of São Paulo and even Brazil have some groups that have been working with the algorithms. We have a thematic project in São Carlos. We have at Unesp Federal of Rio Grande do Norte. So there's some groups that have been working with algorithms, and certainly it can be used in these structures and these machines that they are developing.
Yep. Hello, here. My name is Daniel. I'm from Venturos. First of all, I would like to congratulate you for the pitches. Are very interesting. So about the ion trap, and someone told that we couldn't have here, we don't have here in Brazil the technology to build for a lot of atoms, like 20, 30 atoms. What are the challenges to do that here?
I can, of course, probably this is addressed to me. So I think like the trap that I'm going to build, we can easily go to maybe like 60, 70 ions. I don't think this is a problem to increase the number of ions. But Chris talked before that every time you do some measurement or everything you do in one ion, you perturb the array. So I don't think you have the problem with the fabrication. So I think these days people are working on devices to be able to manipulate them individually and to control them. So for example, you can just keep pushing atoms there, ions, and increase the voltage, keep them together. So at some point you just build a bigger array, let's say. But the issue is that what I noticed is that people probably are limited by the number of ions, because every time they do the operation, they need to correct for heating, and also you need to like do simultaneous measurement on everything. So this is actually not the technology to increase the number of ions that you can trap, but instead be able to control them.
Felipe.
Just a curiosity, continue on his point, what would be the technology needed for do that? I think I missed in the response. What would you need to be able to build the same chip that Chris uses?
Oh, okay. Here that like these groups, like for example, Chris Monroe is a very well-established group that works for many companies, and actually he built himself the company, but actually he works with many companies that are able to design the chip. So here you have like micro fabrications and nanowires and all these stuffs, and then this is actually what people are trying to make things faster. And one of the things that I noticed, for example, for who is starting, it's one of the big challenges is design some device and to have a group that is established in doing this nanofabrication. And this is the challenge actually, because you need to work together. And once you have the product, you say, oh, this might not be enough, or this doesn't work for my needs. And then you do another round of talks. And then for who is starting, so I'm sure these big groups, they have a lot of trials and fails, but they have experiments running to keep the publication. So, and I think here we don't have a well-established group designed for this, I guess. And as he said, actually many of these engineers end up in the companies because when they know how to do, they work actually for a company. So many of these people are not available here in our country to discussions and then try and fail different devices.
I'm Alexander here from FAPESP and at the collaborations team at FAPESP. So could you briefly talk about how you connect with the host institutions that you are now engaging in, and more especially, how do you expect to maintain your international collaborations, either with your institutions that you are coming from or any other partners that you already collaborate or want to collaborate with?
Anyone want to start?
Yeah, for me, there is from this kind of quantum dots that I was growing, there is no many groups around the world that is able to grow high quality single photon sources using gallium arsenide quantum dots. And one of the groups that was the one that I was is not really working now because several problems. And the people, because of this 7 years that I was outside work with Armando Rastelli, I was really included in so many projects that it gave me visibility. And the people know if I have a running MBE here in Brazil, that I will be able to grow these high quality samples. And if I being able to grow this single photon source in telecom wavelengths, this will be very attractive for the people that already know me in this field. And about the collaboration with the São Paulo institutions, I hope that when people see that we have an MBE that is running here in Brazil, the people will approach me, and I hope that the people will go inside this project and help me deliver nice results here in Brazil.
Maybe just to follow, I can keep it going. So yeah, of course, it's always hard to decide exactly where to go, right? There's a lot of variables involved. In my case, I liked the idea of having, there are two groups at the Institute of Physics at USP that could help me to give some support. You know, like one is the group of Professor Marcelo Martinelli and Paulo Nussweig, who have a lot of historic of great results in quantum information, experimental quantum information, right? But also more recently in the Institute, they had a couple years ago another JP projects there that are working with quantum matter under extreme conditions from Valentina and Julio. And so my work is somewhere in between them, you know, like, so I think it can, all of them complement each other, you know, like, and help from each other. And when we think about like wider collaborations, right, anyone who is involved into doing microfabrication, nanofabrication knows that it's a very collaborative approach, because no group can be here or anywhere else in the world. It has all the facilities inside the lab to do all the microfabrication. So we need to have collaborations, right? So that's why I also had to look around what are the options, right? One good option is Unicamp, that has a very good structure for microfabrication. It is not far from São Paulo, so I imagine that we'll be going back and forth, but I want also to help to develop locally and improve a bit the facilities that are already available there. And yeah, and thinking internationally, again, like the fabrication facilities that we have abroad are also usually much more mature, you know, in some centers. So there are a few collaborators that I have done over the years that I wonder, I hope I can keep these collaborations open and hopefully have some back and forth collaboration.
Okay, so the reason, first to going in the first part of the questions, like the reason I choose the University of São Paulo in São Carlos is because they have a lot of history in cold atoms. So the things to manipulate the ions, although the trap for ions to produce the ions are not the same tools, but the everything else to manipulate the ions and to lasers and is the same. So in terms of the equipment, we work basically in the same equipment, and then we can have all these exchange information. There are a lot of experiments that you can do in cold atom system, like neutral atoms, that you can do in trapped ions. And also because they have like along many years, they have developed some techniques for machining parts. And also they do a lot of vacuum chambers and all this stuff. So it's pretty good for us to have a structure from the institute that it's already there. And in terms of the collaborations, one of the ideas that Chris presented before is the idea to how to integrate these systems. So you have a talk before about this, one of young awards. And this is the good point that sometimes you do the experiment with some type of ions, some type of atomic species, and you can do the same experiment. Sometimes the one is more sensitive to noisy, the other is not. So having collaboration also allows you to test and to verify the validity of these algorithms. And this, I think, is a good collaboration, that once you have like many different ions, trapped ions, instead of increase the array to many, many different ions, you build blocks of experiments that they can now communicate. Will be nice. I think not only for us is interested, but even for well-established groups, it's interesting to have this collaboration.
Hans, do you want to take your...
So, so in my case, I'm going to basically try to extend all the possible collaborations with local researchers in the case of the Federal University of ABC, in which I can interact with Professor Breno Marquez and Luciano Cruz, which are involved in the same lab. But also the other point of developing this kind of project in the Federal University of ABC is that the interdisciplinary perspective of this kind of university involves not only the possibility of interacting with the local physics department researchers, but also with other programs like nanomaterials and advanced materials, which in the further steps of the project can be interesting for my project on how to do the engineering and how to use better materials for the designing these kind of sensors. And regarding the international collaborations, of course, I can keep on the collaborations that I have, but also one interesting point of now for us, the awarded researchers, is that now we can get involved in, for instance, international programs that we can act as PIs, which otherwise we couldn't do them like that, right? Now, as PIs of this project, we can get involved with these kind of programs and try to extend our collaborations with other groups in the world, right? So that would be more or less in my case.
Okay, so I think we can all thank the speakers again for their great speech talks. Okay, with a bit of a delay, we move now to the last part of this program. And again, I really thank you all for being here to take part of this. I've heard this was a very packed auditorium for the FAPESP standards. So I think this idea that there is a quantum community eager to be funded in São Paulo is indeed true. So I'd like to just recall that this initiative is dedicated to fostering the development of a quantum technology ecosystem in the state of São Paulo, right? And we believe that this is really pivotal step towards, gathering the community together to align what we believe is the shortest path to a reasonable scientific achievement, but also innovation and technology-driven achievements. I think all the questions that were put forward here for the candidates reveal that there are technologies that we're still lagging behind, and how does the program can help us to address this, and perhaps point to your question on what is missing in the state of São Paulo. I think having a program is one of the things we believe that might help in addressing those questions. So I'll be very quick on overviews. We had outstanding overviews here today. I just wanted to point out one thing. Let me just get my... So I would like to point out with a big if in the beginning. If quantum computers succeed, if quantum communications become reliable enough, if quantum sensing delivers, there is an expectation for a global market that can span all areas of applied sciences, including photonics, semiconductors, cybersecurity, and there's a document from the UK Government Office of Science that estimates a $1 trillion market for this. But again, I'm glad that Chris Monroe, that was in a startup, you know, he was perhaps a conflict of interest in saying so, repeated that, right, if these things happen. On the sovereignty side, I think it's very important we discuss a bit of that and ask the speakers about it, is embargoes. I call it quantum embargo. This is a reality. We don't need to wait for the quantum computers to appear for this to be the case. So multiple nations are putting constraints on export controls on not only quantum computers, but also on technology that are used to build quantum computers. And as you learned from Chris, lasers is one of them. So NATO put out a quantum strategy for the NATO alliance to address the challenges of quantum computation. So this is a big topic everywhere, and we got to the point even that something we don't usually think about, that the airplanes that you're flying in can be hacked. And they have been hacked recently in Eastern Europe. And the question is there room for quantum technologies to protect this hacking to happen? So I think there are various reasons for us to understand how we can position ourselves as a country, as a nation, to address some of these concerns with our own twist, with our own interests. You might be sick of seeing this plot over and over again. I'm bringing it back just to mention two things. One, we are in touch with the company QuTIa to update these numbers. We know from federal funding and state funding that this number is really outdated. This is basically the Senai Cimatec, a center that was deployed in Salvador recently, announced by Embrapi. But I wanted to stress is a contrast with AI. So the numbers in black underneath are the equivalent investment of these countries in quantum technologies announced by the state. I'm not taking into account private funding or anything like that here. And I'm comparing with the values announced for AI research. So you might notice that some countries, some nations are actually investing more in quantum technologies than they are in AI. And Brazil made the right thing, in my personal view, which was to put out a solid program for artificial intelligence. It's the PBIA program, and it was announced by the president in June at the 5th Conference on Science and Technology in Brasilia. And the government is committing 24 billion reais over 5 years to catch up on this era of AI, which is a technology that's already deployed, already in the field. So before talking about the quantum tech, I just want to give an overview that some of you might not be aware. Brazil was really at the core of quantum technologies back in the 1950s. So this is a picture of Robert Oppenheimer it became more famous after Cillian Murphy acted representing him in this movie by Christopher Nolan, right? And there's a very nice paper from Olival Freire that discusses the history of this thing in Brazil. And there was a student of Murphy, or maybe Oppenheimer, very famous one, it's called David Bohm. He was at Berkeley then, and did his PhD under supervision of Oppenheimer. And David is very famous for his interpretations of quantum mechanics. And it turned out that in 1949, the US Congress set up an anti-communist committee to headhunt scientists and other civilians that were involved in left-wing activities. Well, it turned out that Mr. Bohm was very into the left-wing activities, apparently, to the point that he felt that he needed to leave the country. So he got in touch with a friend, Professor Einstein, and convinced him to sort of try to dig in a position for him at the University of São Paulo. So this was intermediated by Professor Mário Schemberg, and then the Dean of the Physics Institute, Professor Abrão de Moraes, and actually Einstein wrote a letter to Abrão highlighting that, you know, he had this fantastic scientist that he wanted to recommendate and asked that, well, he needs a passport, right? And this is the 1950s. There was a concern that he could not get his passport given the relations between the Brazil and US governments. And it turned out that, you know, he asked for the university to intervene in his favor and eventually work out a passport for Mr. Bohm. That turned out to happen. And actually, the most famous paper of David Bohm, arguably, is this one. It has, I think, over 9,000 citations at Google Scholar. And if you see the asterisk in his name, he's quoting now at University of São Paulo, FAPESP. So this is just to put forth that we've been building a community since the 1950s. Professor Moisés Nussenswein attended lectures from David Bohm back then. And Professor Luis Davidovich was a student of Professor Moisés Nussenswein. So I think the whole thing traces back to having perhaps a communist in the quantum science at Oppenheimer's lab. Okay, this is just a story, but this brings me to this slide, which is, we didn't start in 2001 when the federal government really pushed forward the Millennium Institute that seeded the formation, the nucleation of a whole community of scientists working on quantum technologies. It was basically quantum information science. FAPESP on its sides also put forth this Center for Innovation Research that were working on topics that were connected to quantum technologies, even though they were not called so back then. One spin-off of that was São Carlos' whole photonics endeavor was based on this first version of the CPOF. There are glass work, there's many others. So we've been building up this community for a long time. If you want to study that in more detail, I invite you to look over Liliana San's paper that she puts out a map and a network connectivity analysis of how this is, what topics, what research is being done in each state of São Paulo, in each state of Brazil. And we track today that there are over 60 researchers employed at São Paulo State universities and federal universities working on this topic. So this brings me to the program. I just wanted to give you a short historical note on it. So we started this, as Professor Zago mentioned, in 2020. This was a call from Professor Paulo Nussenswein from University of São Paulo to set up a group to discuss what was needed to push forward a program in quantum technologies. So this is the document that Zago mentioned in his introductory talk, and there's a QR code. If you want to read the document, you can just scan it there. And this was putting forth the initial vision we had for what was necessary to create a program in São Paulo. So we didn't know it would take several years for this to happen, but in December 2023, we finally got approval from FAPESP, Superior Council, that a program would be launched on this area. And over the last year, we've been working on call for proposals. The first result you just learned from the young researcher Awardees today. And I would like to emphasize that this was not a work made by 5 people. This was really, we really engaged the whole São Paulo and Brazilian and Latin American community into this program. But I brought these pictures from a meeting we had early 2023, also to highlight a problem we have here. It's really hard to find a woman in this picture. There's maybe 1 or 2. And you might be concerned as well that we did not see any woman awardee in the proposal. Well, it turned out that none applied. So I think we need to really work out, and elsewhere in the world, this is not a problem worldwide. This is a problem here. And I this is my personal opinion, is that world leaders, world-leading universities are putting a lot of energy into hiring the most talented women to their staffs. Rodrigo is an example. He was under supervision of Yuan Chen, which was formerly at Yale, right? And he's now a PI, been very successful at ETH, developing quantum technologies, and there are many other examples. So I think we really need to think throughout the program how we tap into this. How can we make this attractive to have a more diverse gender push in the program? So we highlight a few directions for it: workforce development, strategic partnerships, international relations, like we have now at the University of São Paulo, a CNRS branch that has one of the pillars focused on quantum technologies. There are many others I hope to come, and we are seeking to strengthen those. We're gonna work together with the community on innovation and startups. I think this is something that the NITs, we call, right, the innovation departments at universities have been doing for quite some time. I think it's time for us to get together with them to understand how each university and each NIT can participate in this process of formulating up strategies for innovation startups. And finally, diffusion of knowledge, and I highlighted in red here, ethics. If this is supposed to be what is supposed to be, right? If quantum technologies turn out to be as we hope, we need to discuss how ethically we're gonna handle the problem, or the solution, if you like. So the program was put forth with a steering committee. We have one of the members here in presence, I think Wolfgang Schleich was also on Zoom. Some of the others could not make it. They are in conferences abroad, one in Chile happening right now. And I'm part of the executive committee together with Felipe Fanchini from Unesp Bauru and Ben-Hur Viana Borges. And I would like to stress as well that even though sometimes I'm more on the central role here, Felipe and Ben-Hur have been extremely helpful and diligent to all the demands that show up from day to night in the program, and I'd like to express my gratitude for their support in this endeavor. So just to have a quick breakout of how FAPESP initially conceived the program. It's a 5-year program. Initially, it's actually supposed to be a 15-year program that was approved by the Research Council, but it's going to be broken in 3 5-year iterations. The first 5 years is going to receive roughly 150 million reais investment. Of course, we are always trying to push this number up, but right now, throughout this year, we invested already about 30 million reais, and we hope to keep pushing this in the next few years. So this is what we have on the floor. We just delivered this Young Researcher Award. It was basically roughly 5 awardees, with each receiving about $1 million project. We have, this was finally finished. There was a long discussion with the juridic department of both institutions, but this is finally approved in both ways, and we are just adjusting the calendar for this launch. And I'm announcing here because I think you should already discuss with potential partners from Rio, because this is coming up soon. And FAPESP will invest, I'm correcting Marcio here because he quoted $5 million, I think. This is, well, I hope it will be, but that's not what they signed me for. What I know is FAPERJ is committed 3 million reais on their side to finance research in Rio. FAPESP will put 3 million reais on FAPESP side, but will leave off fellowships. So we cannot add all the fellowships out of this budget. And research consortium that will be 3 consortia contracted with up to 10 million reais grant each. And this is also coming up in January, the call. So you think this is big or not? So let me just give you a perspective on the small pie chart here. So if you take all the Young Researcher Awards, Generation Grant, First Project Grant, these are the grants steered toward young researchers in São Paulo, we have about 46 million reais invested. This is only physics, engineering, so it's a subset of the São Paulo community. So just with this 5 Awardees, we are putting 30 million reais. So even though you might be shy relative to those numbers from the global community, this is a significant addition to what we have already been funded in this area. So we are increasing the number of Young Research Awards by 30%. That's how much you guys represent in the FAPESP's exact science area. So just a few details, so you don't need to ask me. So the consortia, again, 310 million reais proposals. They will be steered, so there will be one in quantum sensing, one in quantum communications, and one in quantum computing and processing. So we want to specify sort of the broad topics that will be tackled by these groups. They will be constituted of 1 PI, up to 4 what we call PPs, which is pesquisador principal. So it's 5 leading scientists and up to 10 associated researchers within of this. So this is to address something that we've seen happening in big grants, that sometimes you have 35 people that are not involved in the project themselves, but just part of the team. So we wanted to make sure that the team sits together and say, we want to tackle this problem and be able to handle the coordination of this. So in total, will be 45 scientists working together on this. And there's some difference relative to usual grants. We'll be allowing short international visits, not only for students and postdocs, but also for technicians employed at universities. This is something that never happened in FAPESP. So if you have a research scientist at the university that's just doing technical work, but needs to be trained or needs to get an upgrade in his career path, you can add them in this proposal. And finally, I want to highlight that we've been discussing very closely with the defense in Brazil, especially the Army, but also with Air Force and Navy. And one of the research topics we want to encourage is defense-oriented applications. So if, of course, you are based in São Paulo, such as Technological Institute of Aeronautics, you are eligible to participate as a QuTIa or even a PI. But if you are not, if you don't have an institution in São Paulo, like the Army doesn't have at the moment, you can participate as an associated researcher. But what we want to bring here is to give this light that there is a path for collaboration between defense and academia, and this is something that has steered a lot of movement in Brasília to put together Ministério de Relações Exteriores and other ministries to drive this partnership. Just a brief note on the FAPESP grant. This will be coming up, but again, it's going to be 1 PI. You decide. This is not restricted, the number of QuTIAs, but it's necessary to have 1 leading researcher from São Paulo and 1 leading researcher from Rio de Janeiro. So this is going to be close to what we call the thematic grants, but with a few restrictions, like the funding is going to be restricted. And this was in agreement with FAPESP. We want to prioritize early career researchers on this. So we define what we mean by that. So PhD from 2012 or later, or 2010 for mothers who delivered, or people that, person that were involved in taking care of someone that is elderly. There's a EDI. I think my time's gone. That's a sign from there. So again, the details will be out soon, as soon as FAPESP decides on the dates that they need to constrain, but this is going to come up in first quarter next year. So I suggest you start discussing this already, so we don't get surprised by the deadline. There's a wish list for 2025. We're going to repeat the Young Researcher Award. So April is going to be the same date, same call. We're going to do it again. So I hope you start to announce it for friends, partners that could be interested in this call. We are working out a strategic partnership with CNRS, NSF, Fermilab have been in contact with us as well, that we are discussing. There's a change in government in the US. We need to discuss that in detail, but there's sign that there will be a strong partnership. We're going to also have a São Paulo School of Advanced Science call early next year for quantum technologies. And this is something that perhaps will address the infrastructure problem, a quantum multi-user call. So we are discussing the details with all the partners involved, but the idea is to put forward, identify local strategic places where this quantum multi-user facilities should be allocated. We've been engaged with CGI. CGI is the Internet Commission from the MCTI that decides where the money from CGI is invested. And they finalized that they want to boost up the quantum technology initiative. The nice thing about this is that people from outside of São Paulo can also apply. So 40% of the grants approved need to be from São Paulo, 60% from anywhere in Brazil. So this is another opportunity for establishing partnerships. And finally, Quantum PP. So this is aimed at startups that want to develop quantum technologies. We will be discussing and handling meetings to address what are the specifics of these calls, but this is something that is a priority for us. And I'd like to end with announcing that 2025 is the International Year of Quantum Science and Technology, as officially announced by UNESCO. So there will be a very, I hope, very, very prolific year. Finally, towards building a quantum community, I would like to advertise something that already started. This is with the initiative led by ICTP SAFER here at IFT, Instituto de Física Teórica at UNESP. We had the first meeting, it was a success. We're going to have a quantum sensing meeting led by Sergio Muniz and Raul Celestrino, which is here, quantum communications, Barbara Amaral and Marcelo Martinelli are here. Quantum infrastructure, it's going to be myself and Rodrigo Capaz from CNPEN that also tackles the problem of, again, infrastructure. And finally, we heard Chris Monroe mention about studying condensed matter with this system. So this last meeting will be focused, organized by Vitor Quito and Eduardo Miranda from Unicamp on how you can look into emergent quantum phenomena with a quantum technology perspective. With that, I thank you again for being here and leave here the website where you can find further information for the program. Thank you very much. I know you're all hungry, but if you want to shoot a question, if not, you can always reach me by other means, but I'll be happy to take any question if you have any doubts about this. Yes, I guess we are very, okay, Dario. Yeah.
About the FAPESP FAPERG that is divided in early and late career, is it possible that, how to qualify a situation in which one PI is early and the other is old?
Yeah, this has been brought up, like whether we should restrict. I'm against restricting, but we have a note in the program that we believe that should be try to push symmetric relations, right? What we would like to avoid is to, in Portuguese you say, colocar azeitona na empadinha do outro. Which is like, you have this big PI that he might not even have time to put energy into the project, but because people hope that his curriculum is bigger and bolder, he will be likely to be approved, and sometimes he's not really involved. So we wanted, that's why we selected 3 for the young ones. We wanted to make sure that the young ones match with young ones. Of course, we're allowed to add a senior researcher, but we wanted to,
so let's say to be young, the 2 PIs must be both young to be qualified as young.
It's not explicitly written there, but it's encouraged to do so. That's what we hope. I think we have enough of the younger community that can do that. I think it's like breaking this paradigm that you always need to find someone much more experienced than you to actually get things approved. We know that's not true, right? Okay. Okay, guys. Thank you all.